We have a very special keynote address. This will be given by Dr. Sadavalu Paparao. Many know him as Pops. I think everyone knows you as Pops, for sure. But Pops has had a long and storied career. I'll read through some of this right now. His research interests are in advanced nanofabrication techniques and leveraging the capabilities of advanced 300 millimeter processes and tools to address challenges in areas ranging from quantum computing devices through terahertz electronic devices to nano biostructures. Previously at IBM Watson Research Center, he co-led a research team that fabricated nanopore and nanogap structures for DNA nucleotide recognition. He also led a team that established robust processes for plated copper front grid metallization for silicon solar cells with improved series resistance and lower shadowing. Since early 2015, he has led efforts at SUNY Poly to fabricate high-performance superconducting qubits using a 300 millimeter fabrication process. And he's also looking at how to integrate the single flux quantum logic devices at this wafer scale. He is part of a team developing semiconductor and other applications of accelerated neutral atom beam technology utilizing this 300 millimeter alpha tool installed by MPC. It's in the SUNY Poly fabrication line. He's also actively involved on the faculty side at SUNY Poly to identify and pursue research funding for areas of strategic interest for the Institute. With that, I would like to welcome, let me flip here, there we go, Pops. Thank you so much.
I guess you can hear me. I want to thank Dr. Hayduck and Ms. Tallman and Laura Wessing for giving me and my team this wonderful opportunity to be here. I must say, I got something from every single minute of the talks over the past several days. And I want to give you, in return for being here and listening, I want to say there will be no equations, there will be no math, so this will be the sort of eating popcorn after you had a nutritious meal for the past several days. So like everybody, I'm going to figure out which way this goes. So, this is going to be, I'd like to take a few minutes to talk to you about where we come from, NY Creates, and then dive into what we're talking about in terms of the acceleration of scalable fabrication of quantum hardware. This is a topic near and dear to my heart, nanofabrication at scale. I always like to tell the story of how there was this researcher that I was working with who said, he had made a chip and there was a serious problem. The copper was getting dissolved all over the wafer. And I said, we can fix this and this is how we can do it and you can make another chip. He said, no, just let's fix this. And after that, we don't need to do it again because I've got my paper in Science or Nature. I don't need to worry about how to make it again, make it better. That's not how we operate. We believe in making sure that it works every time that we are making predictable fabrication processes. So with that said, let me go on. So NY Creates is either the best kept secret or the worst kept secret in Albany. Most people don't know us enough, and I'm here to try and rectify that some. So it is the most advanced, no question, publicly owned semiconductor R&D facility in the United States. In the world, we are one of two, perhaps. You've heard of IMEC, that has a similar sort of scale of operation. And so over the past 25 years, there has been seminal research that has been done at the site. IBM, for instance, which is on the site along with us, produced their 2 nanometer nanosheets out of the tools that are there. The state and companies, Tokyo Electron, Applied Materials, have together invested about $15 billion in the capital equipment that is there. We are blessed that because of these partnerships, not only do we have state-of-the-art tools, they get continually refreshed because we are working together to advance the leading edge technology at our site. So, the Semitech was there. IBM announced their AI hardware center a couple of years ago, and the Meta Center is Applied Materials effort there. And over the next 10 years, they will complete the investment of about $800 million along with the state of New York and to do materials Enhancement Technology Accelerator. That's what the META stands for. So it's a good place to be, and it's the right time to be, and I'll try to bring the larger picture to tie it to the quantum that we are all here to talk about. So, NY Creates has got a statewide impact. We have my colleagues, so our roles in all of these locations across New York State are different. So at Albany Nanotech and at Rochester, we're doing hard work. Not to mean that they are not doing hard work at other places, but at other places, our role is more along the lines of perhaps a landlord, if you will, or enabling the people to do their work. So Next Gen Power Systems is working on GAN, Buffalo, so an immunity biology up in the west end of the state. So we have a whole bunch of operations that are at different places in New York. At Albany, there are many engagement models with our partners. It ranges from the non-volatile memory work, FERAM, and all of those words are real. There are wafers that are running through the line as a result of various partners working on that site, looking at MRAM, FERAM, as well as ReRAM structures. In fact, AFRL, my colleague, Professor Nate Cady, has been blessed by AFRL funding over the past several years to take ReRAM technology into, far beyond TRL2, TRL3. GaN power electronics, there are efforts, like I said, at Next Gen in other places where we are merely helping them succeed at what they do. Heterogeneous integration is a strong effort that IBM has started we basically gutted a fab and rebuilt one for heterogeneous integration, which is the work of the day, the name of the day. I also mentioned the AI Hardware Center, IBM Research. I used to be with IBM some years ago, of course. I don't know what they do inside the Iron Curtain there, but what they are working on, I know from their public presentations, is enabling AI, at 300 millimeter scale, leveraging a whole range of technologies that, you should talk to them to find out. Silicon carbide power electronics, as somebody mentioned in the early days of this conference here, at Marcy, Wolfspeed has built the world's first and currently only 200 millimeter silicon carbide facility. And that got its start by, in a process line at Albany, where we had several years ago took 200 millimeter wafer tools, and then downchucked them to 150 in order to develop silicon carbide process technology. And then when Wolfspeed came along, we removed the downchuck part and made it back to 200 millimeter. They were able to use that technology, prove it out, and now all the tools have been moved out to their facility in Marcy. I believe the engagement was a resounding success. They are happy with the engagement with Albany. Now, the neuromorphic computing, I already talked about that. That is the work with Nate Cady. This is I believe, a tantalum oxide-based structure where they are using the cell into a 65 nanometer node integrated structure. So there is a partnership with Oak Ridge National Labs, with Tennessee, University of Tennessee, working on that. So our interests are very Catholic, if you will, with a small c. The nanobiology work, we are working with a professor at SUNY Downstate, Steve Macknick, where the idea is to create a brain chip that will use photonics to interface with neurons that he has transfected with viruses so that they glow and they're able to receive light in response to calcium channel movement. So the hope is that we address age-related macular degeneration. My father suffers from AMD. All of us know, somebody who's got that. So it's a wonderful effort to be a part of there. And so I won't talk much about quantum in this thing because that is what we're going to do. We're very proud to be part of a place where we think we're going to make a big difference in the nation's efforts to bring semiconductor manufacturing, semiconductor design, semiconductor ecosystem back on shore to the United States and reduce our terrifying dependence on the supply chains that stretch across the oceans. So as you can see, that person needs no introduction. that is the governor of New York State, for those of you who are from out of state. Senator Schumer was visiting us. The tall person there is Doug Gross. We pulled him out of retirement. He was the founding CEO of Global Foundries. We pulled him out of retirement to lead NY Creates, 501c3 corporation. And he is sort of showing off what we do at our facility, right? I mean, behind him, that is an ASM ALD tool. So, the idea is that you want to hit the ground running, and Albany Nanotech Complex is a place where that can happen. There is already, like I said, 150,000 square foot of clean room space, and there are all these nanofab, north, south, east, west, nanofab extension. And then this new fab is our sort of planning ahead to say, we need to have a new fab where the NSTC, the National Semiconductor Technology Center, will have one of its core operations. It is a very large consortium. Oh, and by the way, let me stop here and say, if any of you find yourself in the Albany area, which is just an hour and a half from here, it is probably less than that if Dr. Salman car drives. He gets there in an hour. From Boston, we are about 3 hours away, 3.5 hours away. Let me know. We'll be happy to give you a tour and introduce you to what we are justifiably proud of. This other fab coming there is going to be nanofab reflection, and that is our effort to contribute to the American Semiconductor Innovation Coalition. We hope to be able to respond to the BA when it comes out. IBM, New York Creates, SUNY Poly, a whole bunch of, MIT, there are a whole bunch of organizations that are part of this consortium. And the belief that we have is that we need to use state-of-the-art facilities, right, in order to advance the node, to enable 2 nanometer technology research to happen. And we need to use best known methods for both the structure and the organization. What I mean by best known methods is that at this site, there have been several successful consortia. There have been some that have had more struggles than others, but we can take the lessons learned from that and the best known methods for a successful consortium and apply that to this vitally, nationally important structure. So having finished that broad introduction, and I'll say I have a vested interest in the success of NSTC coming to Albany because I believe it will supercharge quantum. What we are doing now with the existing facilities is going to be much smaller compared to what we want to do. So I'll take just 2 charts to tell you roughly what we are doing at NY Creates. We had a poster, and I think some of you came by to see it. So thanks to support from AFRL and with our partners SEEK, which is a company based in Elmsford, New York, with operations all over the world. We are building fluxonium qubits at 300 millimeter scale using a structure that nobody else has built before. We're doing our build on tantalum-based qubits. The wiring is based on tantalum. The tunnel barrier is ALD tantalum nitride, and then the top electrode is also tantalum. We are basically breaking new ground. When Dr. Mukhanov says, so what is the dielectric constant of this one? Well, we need to figure it out because we have not measured it yet. So we're making good progress along those fronts. And I think, as I mentioned before, with Professor Nate Cady and AFRL support, we've been working on superconducting optoelectronic neuromorphic computing. Now, that long mouthful is to say that we use the superconducting Josephson junctions in order to make sure that we can get speeds that are 30,000 times faster than the human brain. Oh, by the way, I should relate the story. Once at West Point, when I was saying that SONC will be 30,000 times faster than the human brain, Colonel Tim Lawrence was in the audience, and he said, sorry, Pops, I have to correct you. I mentioned that to my wife, and she said, faster than the male brain. So, so we have some things some more speed to capture. But not only is the Josephson junction, the SNSPD is able to get us that kind of speed, but the critical difference which is why this technology holds promise, is that if you're talking electrons, you are going to be limited by the fan out of electronics, right? I mean, from one transistor down to other transistors. Whereas the optoelectronics allows us to basically launch 1,000 photons down a waveguide and then split them off into, let's say, 1,000 SNSPDs, single photon detectors that are cryogenic. And so now you are able to, in the fullness of time, we're not there yet, connect one neuron to 1,000 downstream neurons. So that I think is what distinguishes the human brain from all other implementations of neuromorphic computing that are out there. Reservoir computing is interesting, of course, but in neuromorphic computing, where you have a 1 to 1,000, now we're close to what our brains are doing in terms of the interconnection. We are also working on engineering the surfaces in order to replace native oxides with engineered oxides to improve qubit performance. But, and a few others. In the interest of time, I want to, there's no clock here. So, Dr. Haydock, anytime you can, oh, there's the clock. Good, thank you. So then maybe, with RIT, Professor Stefan Prebel, and with Mike Fanto, we were working on ALD aluminum nitride. Unfortunately, I'll confess, we gave them ALD aluminum nitride that was cracking badly. So the tool is currently sulking. Once they get it back up, we'll be able to get wafers back out and prove this important technology. The idea being you want to be able to modulate light using ALD aluminum nitride waveguides and get them to interface with trapped ion qubits. We are also working on niobium nitride and tantalum nitride nanowires. The idea being they can work as high kinetic inductance structures. They can also work as SNSPDs. They can be used in SFQ circuits. So the advantage is that there is a synergy in technology development between all of these, so everything feeds off of each other. The reason I put these pictures is to point out the name of the game is 300 millimeter. We want to work at 300 millimeter. We want to work with people that are developing other technologies and help them get to 300 millimeter. And so, we want to make sure that our wafers look as beautiful as Dr. Ekta Bhatia's wafer that she produced there, all the way from the center of the wafer to the edge of the wafer. Here is our CD is mumbo jumbo for critical dimension. It is the width of the line that you want to monitor. There is a RI, reactive ion etch process-driven variation across the diameter, which we can improve. But even with that variation, it is basically 5% 1 sigma across the whole wafer. And then down here in the bottom right is a picture showing CMP, chemical mechanical planarization processes that we use, which give us an ability to integrate these fluxonium qubits with surfaces that are much more planar. So you can deposit 200 nanometers of tantalum and it'll be very rough. But after CMP, it is very smooth. And so we think we can improve our performance as a result of that processes. Now these features here, those are dummy fill structures. You need to put them in order to make sure that CMP proceeds properly. The other thing that I want to show in the figure at in the middle is what you get as a easy, by the way, when you are operating in a 300 millimeter facility that we share with the industry behemoths, right? We get process control. This is data that we have acquired on various wafers that we're running for our projects at the bottom electrode lithographic step. And over the course of 3 months, you can see that our variation is like, plus or minus 3 nanometers, 1 sigma. So we are we're able to produce predictable fabrication results. And I'll come back to that because that is important. So this is an eye chart, but I want to drive home the point of the synergy that is there. So if you have access to superconducting materials and cryogenic dielectrics, high kinetic inductance materials, and those are the actual materials that we're working on. Sorry, I forgot to fix that. There should be PVD tantalum nitride or ALD tantalum nitride. We can make all of these variety of individual devices, with the idea being we are driven by the right side of this chart. We are driven by developing technology that has meaning. So, rather than merely saying, okay, we produce one chip and it doesn't work ever again, we want to make sure that they work repeatedly. We want to produce high Q capacitors so that we can shrink the size of the qubit down by a factor of 10. We want to use them for photonic computing, atom interferometry, and trapped ion chips. all of our characterization is done in partnership with other people that have deep expertise in that area. We are fortunate to be connected to AFRLs and the Innovare Center. So you will see that they've got cool dilution fridges coming out of their ears here at various places, as well as at other sites like Auburn University and so on. So, having talked to you about that, now I'm going to get to the meat of the talk. So how do we want to accelerate scalable hardware? And I think the best thing is to say we need to learn from history, right? I forget who it was. Was it Churchill who said those who don't learn history are condemned to repeat it, right? And so I put this on. It was only this morning that I realized I'm going to a DoD sort of lab and I'm going to talk to them about weapons. So this is like taking coal to Newcastle. I apologize. But this is a fascinating story, right? Eli Whitney, whom I knew before as the inventor of the cotton gin, his other major invention was the interchangeability of parts in the musket, right? And so one of the reasons that I believe the American revolutionaries were successful is that when a musket failed on the field, they could repair it a lot more readily thanks to his invention. He couldn't patent it, apparently, because it was such an easily copyable invention that other people did it too. But I guess we have America to thank for the result of that, because you guys were an independent nation. It took us Indians another 200 years to get out, but anyway. But the idea of interchangeable parts is critical. And what is interchangeable is that it is manufactured to a specification, right? You want to make sure that when you get it off, it works the way this person told you it will. And that is one of the things that we learned that we had to apply. The other thing, of course, is the assembly line, right? I mean, the fact that you need to have a process that is highly tuned to make sure that it does the same thing over and over again. And of course, things go wrong when Lucy is involved. But the moving assembly line is an innovation that we have incorporated. I don't mean to say we're not using it, but we need to bring it into quantum is the point that I want to make. Right now, a lot of the quantum research is being done in ersatz sort of ad hoc tools. So we need to move to the point where quantum engineering is not, a term that is bandied about by a few people. Quantum engineering is here. It is already here. I mean, as a graduate from MIT, I believe that engineering research is not an oxymoronic term. Engineering research is critical. And I believe that the US is great at basic research. I wish that we did a much better job at that research that takes it from that basic research level before it goes into the manufacturing workplace. There's a lot of work. The valley of death is perhaps the wall of fear, because the cost of doing technology development at scale is rapidly rising. And the risk hasn't decreased. And by the way, this is not my idea. I picked this up from Jim Mesovich at BNL. He said if you multiply the risk that is still high because the technology is still immature, with the costs that are rising because now you've gone from onesie twosies to making a large number, that product is the wall of fear that companies have to cross. And so I believe that an STC is one step towards making sure that that doesn't impede companies in the US. So, the assembly line and the modern fab is an example of an assembly line that, that takes a piece of silicon and produces chips at the other end. And so we're using that. We need to bring that into quantum. The other thing is reliability in fabrication, right? I mean, we cannot be satisfied with making things that don't last. I won't quote the paper, but it was, my jaw dropped when I read this one paper. It's old, and clearly it was early days for quantum, but it said, well, we take this part and we shipped it twice across the country and it still worked and therefore it is reliable. That cannot be the way in which reliability is assessed. So, I deliberately blanked out those car names, right? But we know what reliability in fabrication has meant in terms of cars. And one of the other stories that I want to relate to you is, I was talking to this guy who was in the semiconductor industry, but he came but he was in the car parts industry before. And he said, as you go along, I forget is it I-80 or something that goes from, Illinois down through Kansas or whatnot. So there are very many companies there, but he can see the difference in philosophy between different companies in terms of quality. And the reliability that we call quality in the final part comes because the factory is investing in making sure that the quality happens. And how does it invest in that? He said there are companies that will say they are going to change a particular gizmo, a lathe, part of a lathe, when it stops making parts exactly to a much tighter spec than another manufacturer that is willing to take some early infant mortality in their parts. So there is an investment in reliability that we need to do. In quantum, what does that mean? We need to make sure that we develop the metrics that are necessary for characterizing reliability, right? I mean, the semiconductor industry here, for instance, you cook it at 105 degrees centigrade, you apply a lot of stress, but clearly when we're operating at millikelvin temperatures, our considerations are different. And so the basic science that needs to be understood needs to be changed. Thermal stress, and I think, a short while ago, I was talking, I think with Dan Campbell, about when you take a part and cool it down, how do you make sure that the alignment stays, and how do you make sure that it works? We want to make sure that when you cool it down and bring it back up to temperature and cool it down again, it stays working. I mean, the story I heard from Eric Holland, who joined us from Yale, he said, many students fabricate a qubit, they cool it down, and they don't want to heat it up because then their PhD is dead. Because you want to make sure that things don't shift because of a cool down, cool up cycle. I'm relating a story. Hopefully, we don't do that with our devices. The other thing, talking about history lessons, right, for quantum engineers, we as an industry have got to embrace change. The ITRS, the International Technology Roadmap for Semiconductors, this of course postdates some of those pictures in there. And the point I want to make is that the very first transistors that were made were not even based on silicon, right? They were based on germanium. And then soon, when silicon came along, a jump was made to say, how can we do this better? So I believe quantum is in a ferment, right? There are so many ideas that are going along. Now is not the time to pick winners and losers, right? To figure out whether or not photonic qubits or superconducting qubits or ion traps are the best and the only thing to invest in. The idea is to recognize that quantum systems will be hybrid, that they will be the best portions of various technologies that are employed in a system. And then over time, clearly there will be a shakedown, but we need to make sure that we embrace that change and not shy away from it. So this picture, I picked it out because that was a point contact transistor or whatnot. And then we abandoned germanium. We went to silicon BJTs. And this is the chip that flew us to the moon, I believe. And then, of course, we abandoned BJTs. And we went to MOS devices, single, not CMOS yet, right? And then we went to MOS, and then we went to CMOS. So there has been a continuous change in technology that we need to keep in mind. The other part that is important, and luckily I don't feel like the voice in the wilderness crying out, right? Everybody recognizes that we need to create levels of abstraction so that the material scientist doesn't have to worry about the system level consideration, but each one of us makes a commitment as to what is going from one stage to another stage. And then we deliver on that promise, on that commitment. So if you are a system level designer, I'm certain you have no clue what is happening at that interface, that a material scientist has got to worry about. And likewise, as we go from these things, we increase the efficiency of the organization because you can apply people's learning to what they know and we can communicate in a common language. This doesn't exist yet in quantum. The other point is the predictable fabrication. If you say, I'm going to make a transistor and it's going to behave like this, it is because you have predictable fabrication. If you don't have it, how are you going to be able to make the promise that tomorrow's devices are going to behave the same way? And this is where 300 millimeter comes to the rescue. It is less to do about wafer size. In fact, it has nothing to do about wafer size. It is more about the fact that 300 millimeter tools represent the pinnacle, current pinnacle, of semiconductor technology. Everything that is the best in best in the tooling, process control, is embedded in a 300mm tool. Here is an example of a CMP process. Some of you would know. It's a reflectance monitor, so you don't need to worry about CMP it a little bit. Oh, it doesn't look good. CMP it some more. No, you are able to use an in-situ monitor that figures out what the actual endpoint of the recipe is. In addition, there is another variant of this endpoint monitor, which actually adjusts the pressures of the various zones across the wafer so that the wafer comes out exactly planar and exactly the same thickness across the entire 300mm wafer. So these are processes that are there. What is the other important thing that is necessary for predictable fabrication? Not only about capability, but control to give you higher signal to noise ratio. I mean, and granted, quantum is moving. We are not there producing millions of qubits yet. But at this stage, what 300mm process tools give you is signal to noise ratio. So you don't need to repeat experiments too many times to know that you've got that. And then PDK, process design kit development. If you want to design a kit that a designer can use, a process kit that a designer can use, it's called a PDK. You need to say, when I make it this way, or when you design it this way and you follow these rules, it will come out this way, right? And so for that, you need process control. These abstraction that I'm saying we should do, and I know I'm preaching to the choir, but it is harder in quantum, right? I mean, as the chief scientist was saying, digital, we love digital. You know, there's a lot of signal noise margin between 0 and 1, whereas when you go from digital to analog, there's a lot more to specify, and that is the OIP3 point, and you need to worry about, frequency, you need to worry about noise. And when it comes to quantum, not only that, we don't even know what we don't know in some cases. So we need to study, what are the effects of native oxides? How do you control that? What is the participation ratio? How does that affect when I change the material through engineered oxides like I want to? What about the materials? How do you characterize it? Spatial extent of the model. What I mean by that is, at least in digital devices, the signal goes to here to there, and you don't need to worry about the large macroscopic environment. But if a microwave photon from a qubit exchanges energy with a TLS density, TLS state somewhere, 2 microns away, you have to worry about it because it makes a difference. So these are all the things, the speed, the frequency, the noise behavior. We heard several people say in the first day of the conference that noise was considered, so bad that the designs were heavily conservative. But if you know the nature of the noise, it's not white noise, it's colored noise, then how can you change your quantum algorithm to take that into account? Cosmic rays impact, right? I mean, Martinez had this very nice paper about using normal metals to reduce that impact. And also the question of variation over time. So lots of challenges that need to be made, but luckily, there are people who are already working on it, much smarter than I am. Mark Ritter at IBM, Mike Chuang from MIT, Isaac Chuang, and Jim Misowich. There is a team in C2QA that is working on abstract machine models that'll take, all the way from devices from materials to devices to chips to algorithms, looking at, what is the connectivity that you have and how can that be co-optimized, co-designed with the algorithm that is there? How can you trade off between yesterday, the speaker and from NRL was talking about state preparation measurement. How do you create a problem that doesn't take inordinately long for the quantum states to be prepared before you're able to utilize it? How do you think about nearest neighbor interactions? There was several talks talking about if you have photonic material coming here and you've got a qubit here, how does the microwave photon interact with all the TLS that is in the oxides? Or the question that was asked about phononic poisoning of superconducting systems if you've got an SFQ system on the same silicon plane. So people are already thankfully thinking about it, but we need to supercharge this effort in order to make sure that we can accelerate growth. So why is PDK, just if I needed to convince you of that, this figure perhaps from the semiconductor industry points it out. What PDKs will do is democratize access, right? It will allow fabless companies, just as it has allowed fabless companies to design anywhere, wherever they are, Hawaii. and then have their chips made in other places. Having a quantum PDK that is robust will be very useful. And again, is already happening. Dr. Fanto yesterday was telling me that soon their team will be developing a photonic quantum PDK in partnership with AIM Photonics, utilizing the 300 millimeter wafer fab at Albany to do exactly what I've been saying, but in the photonic regime. So things are already happening, but time's a wasting, as they say. So we need to do more of it and do it faster. So I mentioned the fact that the open PDK will decrease the barriers to entry, right? Startups and academia. What are the other things that we can do? Currently, I feel that an open PDK that allows you to see deep inside the device. You have access to the PDK, and if you say, oh, I just want a transmon here, and you can do that. But what if you want to know, well, what are the characteristics of the transmon? So we at NY Creates are committed to keeping an open PDK during our development. We should have multi-part wafers so that people can test their ideas out at 300 millimeter scale, much like AIM Photonics is doing already. We need to create an open test bed, which I think Innovare is a wonderful place where such technologies are available, and more patient capital investment, right? And so one of the things that NY Creates, my colleagues are doing is they've created what's called a corporate venture exchange, where corporate venture tends to be a bit more patient than venture capitalists typically are. Not that I should besmirch them with one broad stroke. There are, Playground Global has invested in PsiQuantum. They are looking far ahead. But I think getting a larger pool of such patient capital would be good, and collaborations need to be deeper, because it is in collaborations that new ideas and inventions happen. And so that's what we need to be doing. So with that, I want to thank you for your attention. I want to thank our current active partners. There are many other partners that I'm fortunate to be involved with. I hope to add your name to our list of partners. Thank you, everybody.
If you use a single flux quantum circuit on the same plane as, I would assume you're talking about a superconducting plane for qubits. Can you explain that?
Yeah, perhaps I misspoke. I meant to say phononic poisoning.
Okay, I wrote it phononic. I wrote it phononic and said photonic.
So if you've got an SFQ circuit on the same crystal plane, as it is switching, it is liberating energy. And this is a paper that Britton Plord and I think Oleg Mukhanov and the others were exploring. And I'm basically quoting what Britton Plord said at Syracuse University. So when a phonon propagates from the SFQ portion of that chip to the transmon portion of the chip, now it is creating decoherence mechanism. So that.
Other questions?
Oleg, anything I should have added? Is that?
Well, once people realize that, they immediately find a way how to mitigate that by placing SFQ circuits which have Josephson junctions which switching, and the transmon circuits which have Josephson junctions which do not switch. They are nonlinear inductor on different chips. And once they're on different chips, then phonons cannot easily travel through. That's one thing. Other things was to add special structures, normal metals, etc., and different gap materials to trap quasi-particles before they can reach qubits. And Syracuse University have active research in this area, and they're making quite good progress. So it's a small, I would say, small effects, but again, universities are happy to investigate that and treat it to maximize the efficiency.
Thank you. Thank you.
Dr. Zepp, do you have a question?
I'm as a supporter, all the partners, collaborators, competitors.
So IMEC is a partner, and I think particularly we have been exchanging ideas about how we can work together to make niobium nitride, tandem nitride, niobium nitride SFQ circuits along with them. There is also an effort to figure out how we can work together on EUV lithography, because clearly it is easy to declare yourself a competitor and say, we don't want to talk to you, but it is far more efficient and effective to find ways in which you can work together, and we are. So at least in the quantum space, where I'm leading the interactions, we have a fruitful collaboration, nucleated.
I have a general question. I was curious, what fraction of your operation is devoted to the quantum space, and how do you see that growing, say, in the next 5 years?
Oh, I'm very greedy, but right now it's a very, very small fraction. I mean, I'll be open with you. I have a whip corridor of 15 wafers, right? And there are 10,000 moves that happen every day. And so we are lost in the decimal space. But my hope is that as we continue to grow, we should be able to make a significant fraction. We'll never be the dominant, I think, but we don't need to be. Like for instance, there are some tools that we have specifically modified in order to accomplish things that are more quantum-y, but we can still run side by side with the regular process, for CMOS technology. So we can share.
There's been a lot of talk this week about workforce, and I saw in one of your early slides that you get about 2,700 people, or more than 2,700. I assume that's across all the locations. When you look at either scaling for quantum or reshoring of microelectronics in general, what do you see as being kind of the top critical needs as far as workforce, whether it's respect to engineer scientist versus technician, and/or kind of aging and retiring personnel currently on staff?
Thank you. I mean, I must say, I didn't ask you to ask that question. That's a very, very good question and an important one. So one thing, the 2,700 is at that site, but it is not all NY Creates. IBM has got a strong group, Applied Materials, Tokyo Electron. So on that site, there are that many people. So across New York is probably greater than that. I do not have that number. But to your question as to what needs to be done and what perhaps we're doing, we are fortunate to have a great partnership in Professor Bob Geer at SUNY Poly at CNSC. He has an NSF-funded program called NYSTEC, Northeast something or the other. But he has been working over the past several years now, honing the model to work with community colleges, with recent grads, high school grads even, and those that are interested in technician trades, to give them exposure to 300 millimeter wafer fabrication, should they be interested in that area, and to grow, into that. So if you've got a GED, yes, you can work in a fab. If you've got, a slightly more advanced degree, you can also work in the fab. The pathway for engineering and master's degrees is perhaps well thought out already, right? I mean, so we are working with people that are graduating, looking for master's degrees at SUNY Poly, at CNSC, or other leading institutions, of course, as well as PhD students. The pieces that I feel are missing that we need to increase are the idea of quantum engineering, right? I mean, and again, MIT has a quantum engineering course that has started. Yale is thinking of doing it. I was talking to Professor Steve Gerwin, and he said he's revamped his entire quantum mechanics course that he teaches undergrads to change it from teaching, Schrodinger's equation and how to do the hydrogen atom, to starting from a quantum computing aspect of it, because he said, these were his words, a lot of the weirdnesses that we associate with quantum mechanics can be taught in the context of quantum computing. And so they are flying into the driver's seat, if you will, of where we are right now, quantum 2.0. The other important thing that is perhaps missing is entrepreneurship mentoring. And that, again, the CVX and other things, NSF I-Core is an example. But we need to find ways in which we allow companies to succeed faster, or more companies to succeed, crossing that chasm with advice on how to scale that technology. If I can take one more minute, the idea is there are so many people that I talk to, they say, oh, we have this way of making XYZ, a qubit, a nanopore, and then we want to make it at 300 millimeter scale, and we want to do it exactly the same way. Unfortunately, that never works. And it is similar to the learning that I'm familiar with when Intel, TI, anybody, we have always struggled to translate technology developed at 200 millimeter to 300 millimeter, or from 150 to 200, or from 4-inch, because at that time they were calling it 4-inch wafers, 4-inch wafers to 6-inch wafers. Because you always have new opportunities, new ways of doing things, new tools, new processes that you want to reinvent. Similarly, entrepreneurs that are developing technology should be given a handhold to say, this is how you can scale your technology and make it easier to fabricate in a global foundries or Intel and so on. So I hope I answered. Thank you.
Thank you, Pop.
Thank you very much.
All right, so you've heard a lot last few days about partnering and collaborating and what that means to AFRL and how important it is. And Dr. Linderman kind of hit that point home earlier today. So with that said, we decided to have a talk this morning on actually how you work with AFRL and how you are able to work across international lines. So we have the honor to have Ms. Rebecca Mills with us today. As you see, Becky is the Senior International Focal Point at AFRL in the Information Directorate. So she's responsible for all of our international programs within Rome, and she oversees all that work that is going on. So a little bit about her background. She's got a tremendous research background. She started with us in 1990 out of the University of Rochester, and actually worked with her back then. So I can talk about some of the research she did back then in photonics, which is so key now that we've been talking about the last few days in terms of optical memory, electroabsorption modulators, photonic analog to digital converter circuits. She then moved on to work several acquisition programs for us. So as that technology, different technologies transitioned and moved forward in the acquisition process, she was actually able to move some of that technology out to the warfighter. So, really important for us within the Air Force in terms of transitioning those technologies. At the same time, she also did a stint, worked as liaison for AFRL with the Chief Scientist at Air Combat Command, or ACC. Again, seeing how technologies that we develop within AFRL, within the Information Director, can affect the life cycle and the acquisition of the Air Force systems. Finally, I'd like to acknowledge that Becky is a AFRL Fellow, which very small percentage of our scientists in engineering and technical workforce. It's only 0.3% are awarded that honor. So it's truly great to have Becky with us. All that really put Becky just in the perfect point in her career to be our focal point for international programs. So Becky, the floor is yours.
Thanks, Mike. That was a surprise. I wasn't expecting such a nice intro. So thanks, everybody. I'm happy to be here. We're going to change gears and talk about how you can work with AFRL. And the focus is on the international side. It's very similar for domestic, but international is a very interesting aspect, and not a lot of people understand the process. It can be pretty confusing. So I'm going to kind of lay out some of the mechanisms that we have in place that allow us to legally partner with international entities. And oops. So the first question I'm always asked is, well, how does it start? How do you work internationally with AFRL? And it starts in all kinds of ways that, when you think about it, is pretty obvious. But in groups such as this, conferences, journal papers, where you meet people face to face, you start talking, you interact, that you discover interests that you're all have in common. It can start with an engineer at the lab knowing a professor at an academic institution and wanting to grow that relationship. It can start with an S&E, a scientist and engineer volunteering for an exchange program. In those ways, it's kind of from the bottom up, you know, the onesie twosie engineers working its way up. And another way it happens is top down. So as our defense leaders have strategy planning meetings, they realize that there are certain nations that are very important strategically, and they want to partner with them. And vice versa, some of those other nations want to work with the United States. So sometimes it comes from the top, from the Office of Secretary of Defense, and when these defense agencies get together, the flag officers will sometimes and often say, hey, we want to work with you and we're going to work with you, make it happen. So then it all filters down to the lowest levels at the laboratories, which is us. And their scientists and engineers and our scientists and engineers get together, we kind of explore areas of what would make sense to actually create a project and collaborate. And sometimes it happens at the lower level, but from a top person, top leader, such as a technical director at chief scientist, like Dr. Lindeman, or our director. They may have colleagues that from their career that there's a niche that they know about, and they come back and they tell our engineers, work with this group. And so from these different types of conversations is how it starts. And so when you think about it, it's kind of obvious, but it doesn't really dawn on people. That's the actual starting point. Okay, so there's two ways that AFRL and the government works together, and it's basically the government, AFRL, working with non-government entities, or AFRL working with other government defense entities. So right now I'm going to talk about the government, AFRL working with non-government entities. And these are, basically industry, small businesses, and academics. One of the ways that we are legally allowed to collaborate with non-government entities is what we call a CRADA, Collaborative Research and Development Agreement. And ICRADA is for the international way of doing that. Very similar to the domestic way, a little bit different in the approval processes. But for those that don't know what a CRADA is, it's a collaborative agreement where there's no money exchanged, but each side will come together and say, create a project plan, and you agree upon who's going to do what independently, who's going to do what together, where are you going to do it. You know, you just lay out your project, and so because no money is exchanged, there is a cost associated with it that gets tallied, and it's basically the cost of your personnel, the cost of the development of what it is that you're going to be working on, equipment, cost of facilities, things like that kind of get calculated and put into the CRADA, but there's actually no money. You just need each side to commit to agree with what you're going to do. And then the paperwork, once the engineers get it all situated, it goes up to Secretary of the Air Force, and they do their thing, they iterate on it, and they'll hopefully come back with an approval. So next way is with working with our sister directorate, AFOSR, the Air Force Office of Scientific Research. That's the basic research arm of AFRL. We work very closely with a lot of the program managers there. Some of you may be familiar with AFOSR, but we can co-fund with the AFOSR program managers here from the lab and work with them and to provide a grant. A lot of what AFOSR does is fund their own portfolios and they have an outreach. There are several international offices. There's one in London, there's one in Tokyo for Asia, there's one in Santiago, Chile. There are 2 new offices coming online. I'm not sure of the exact status, but they're only going to be manned by 1 person. So initially getting their feet going, it may be hard. So that will, one of those is going to be in Sao Paulo, Brazil, and the Chile office will be helping until they can get a little bit more established. And the other office is in Melbourne, Australia. And right now, Tokyo is helping that office out. So we have this outreach, and we can work with those offices to help us find key players, not just for quantum, but across all the disciplines that AFRL works in. And the third thing is cooperative agreements. These have been around a lot. The Army uses them a lot, but they're a new discovery for us, and we're still learning how to do them, but it seems like they provide a very great alternative to work with academic and industry. So it's like a grant where the US AFRL will fund the entity, but the work plan is created in lockstep with the AFRL program manager. So it's almost like a mix between a grant and a CRADA. So it's collaborative in nature with our scientists and engineers, but we will pay that entity. It's run through our contract shop. There's different types of rules and things that we're still learning and figuring out, but it's an avenue that is opening up to us. Those are the 3 main ways that we can work with non-government entities. There may be others, there are others here and there depending on what the situation is, but this applies mostly to hopefully some of you that may want to work with us. So now switching gears over to AFRL, a government defense agency working with other defense government agencies. So the first thing that is required is what they call a memo of understanding. This is a nation-to-nation agreement for defense purposes in our case. There are many, many, many nation-to-nation agreements for all types of partnerships. For our purposes, it's for research, development, technology, and engineering. So we have to rely on either existing RDT&E MOUs to work with a particular nation, and if one doesn't exist, we have to work with our defense departments to try to create one, and they take a lot of time. These MOUs are, they provide the structure and the framework to guide and dictate what is allowed to do with that nation. And they last for 25 years, sometimes longer. They can be classified, and they can be bilateral, one nation to one nation, or one nation to many nations. But that's what's required for this, the first step. So when another government comes to the United States and says we want to work with the Air Force in this area, that's the first thing that we do, is look to see what existing MOUs are available. Okay, then The types of things that I mentioned, they dictate what you're allowed to do. And these are things called project arrangements, information exchange or data agreements, engineering, science and exchange programs, equipment loans, personnel exchange agreements, things like visitation is allowed for long-term, things like that. And I'll get into these coming up, but the project agreements are just that, an exact project that is created with the other nations' scientists and engineers, and they can be bilateral or multilateral. The information or data exchange agreements, those two terms are actually synonymous. They mean the same thing. They used to be called data exchange agreements. It dates back many, many decades ago. And as the world has changed and evolved, data was too confining because you just think that you're just trading data. Really trading information, data, knowledge, anything other than money is what these agreements allow you to share. And they're non-collaborative. The data and information agreements are just that. You share information, data, whatever it is that you're working on, but they're not collaborative where you're working together on a project. Those are project agreements. Okay, so I'm gonna talk about each one of those a little independently, and I know some people like hate animation, but I added the animation here because there's so much it gets confusing when you see it all at once. So I just kind of broke it down. So if a nation says we want to work with AFRL and quantum, we look for the existing MOU that allows research and development with that nation, and then we meet and you explore different areas. And this is, again, government, not academic, but government scientists and engineers. And you kind of explore what you want to do. And you create a project. It can be bilateral. If it's bilateral, it's like usually a 50-50 contribution. If it's multilateral, it's equivalent. If it's 3 nations, it's what, 33.3% or whatever adds up to 100. And it's not necessarily cold hard cash. If the United States has more cash going towards development, but another nation has a test range or facility, that is their main contribution, it's all tallied up. You tally up financial and non-financial contributions. And if that total is equivalent or equitable, then that's what will work. And so again, you need that overarching MOU to be in place to get that project agreement in place. So for the data and information agreements, exchange agreements, again, these are no personnel working collaboratively. There's no money exchanged, but the equitability is calculated in a quid pro quo type fashion. So that information exchange has to be equitable and beneficial to both nations. You can't just have one nation sharing all of their secrets and all of their information and the other nation not contributing. It's got to be a mutual benefit. Now that there's specific MOUs for exchange of personnel for our scientists and engineers. This started out as a 2-year commitment. It's a program that's run by Secretary of the Air Force. Our engineers would go overseas, or someone could come to us for up to 2 years. It's boarded, so our engineers have to go through a board selection to determine if they qualify. Language is taught if required. If you're going to Japan, they'll teach you Japanese. And there's a new pilot created that allows for a short-term version of the 2-year visit, because we really weren't getting the personnel wanting to do such a long exchange. And then there's other collaboration avenues that I'm not going to focus on, but I'll just mention. One is called the Technical Cooperative Program, the TTCP. This is a Five Eyes nation-centric collaborative partnership. And the other is, of course, NATO nations in the Scientific and Technology Office. If you're a NATO country, there's projects, collaborative projects, studies, various activities that are performed. Real quick. So we talked about the engineering exchange personnel. We have 16 nations that we partner with to exchange personnel with. And then again, the STEP is a modified version of that 2-year program. To get approved, our engineer would, so if someone's coming to us, our engineers would work with that person. We would receive their resume. We write up a description for the position and the work that they're going to be doing. We get the supervisor to approve that, yes, they'll be part of the team. Several different types of paperwork. We send it in, send it up to staff, and the person can come in for a long-term visit, or we can go overseas to an institution up to 179 days. Another way to bring in exchange personnel is with those project agreements. You can write into the agreement that you expect to exchange personnel. We'll send someone to up to a year to another nation, or we expect them to come to us for up to a year, or however long you want. You write it into the agreement, and that's called Cooperative Personnel Placement, the CPP program. It's got to be written in that agreement. Something that we're trying out that's new is this innovative teaming. This is specific to the UK and the DSTL labs. This is looking to try to bring small teams of people over to the UK and work with them. It's roughly new, a couple of years. We have the Windows on Science program. This is in partnership with our AFOSR directorate, and some of you traveled here on the Windows on Science program. This allows us to bring in an academic for up to 10 days, 2 weeks, to brief what your research and have a little seminars that we can learn and potentially have some conversations of working together in the future. AFOSR will support and sponsor your travel, I think up to a certain dollar amount. And then Windows on the World is for us to go overseas up to 179 days in a similar fashion. So the top few there are government to government exchanges, and the bottom 2 are for academic exchanges. The listing of the nations that we have agreement with to exchange personnel. If your nation is not listed, that's okay, because we can use one of the other vehicles, such as an international CRADA, to create an exchange and agreement with you. So I laid out the first step of it just starts at the bottom or the top down for how an agreement starts, but that doesn't really tell you much. For the information director, it actually, if someone is interested, they contact me. And I work very closely with our headquarters and with our Secretary of the Air Force. And when an interest is raised, the information will come to me, or I will push it up. And then from there, we will help create and facilitate information exchange meetings, and help work with the engineers to start that process of creating a project or determining which pathway is the best way to move forward on. And then everything is template-based just to make it simple. So we bring the people together, and after the conversations kind of have filtered and you kind of know what you want to do, we use these templates to put your brains to paper and get the project written. I liken it to writing a proposal. It's a short proposal. You know, how much time, what are you going to do? What are the tasks? What are the goals and objectives? Blah, blah, blah. Very similar. I think everybody is familiar how to do that kind of stuff. So we just help you fill it out in the format that Secretary of the Air Force requires. And it goes back and forth. So this is the bad news. None of the collaboration work moves along quickly, but we are trying very, very hard to reduce these timelines. This shows a timeline expanding 2+ years from very start to very end when agreement is signed. It doesn't always take 2 years. This is kind of a worst case scenario. The hardest part is these two front blocks. It's getting the engineers and the scientists together and getting your brains on paper, like I said. It's iterative and working internationally. Sometimes it's hard, especially it's easier when you can meet face to face. And the past 2 years have really been detrimental to doing that. And yes, we work through email, we work through virtual means, but sometimes just getting together in a meeting like this, we can go off to the side and really nail out and finalize some of these template documents. Once that gets done, I take it and help the engineer get it through the directorate for approval from our director. Once that's done, it goes over to our headquarters. Our headquarters takes our documents and turn it into the actual draft agreement. By law, we're not allowed to actually share the agreement with the other nations, so we create these templates that elicit the information that will be put into the actual agreement. So headquarters then turns this paperwork into the draft, and then they staff it over to Secretary of the Air Force office. Secretary of the Air Force takes it, they do what they call a murder board on it, and redline it and come back and forth with a million questions and clarifications, and you have to do this once the lawyers get involved. And then once we get that done, then we sit and wait. And at that point in time, we actually can't talk about the agreement with our cohorts in the other nation. So we just sit and wait and let the negotiation process happen. And sometimes I've seen it happen in 6 months, sometimes a lot longer. But we have been trying to really make it from when staff receives it to nation signatures to be about a year. So the quicker that we can reduce this 1 to 18-month process in the front, the quicker we can get an agreement really staffed and signed. Then when the agreement becomes effective is when the very last nation, if it's a multilateral nation, the last nation signs. The date that they sign is the date that it becomes effective, and however it's written out in the agreement, whether it's a 5 years or 3-year agreement, starts from that date. So then the groups will get together, have a kickoff meeting, and at that kickoff meeting is when you sit down and you really do your project plan out in detail, your milestones, your schedule, all your detailed tasks, what you were thinking about doing maybe 2 years ago. Technology moves really fast, especially in the software domain. Things might be out of date. So you revisit what you were gonna do specifically and massage it, make your plan and get going on your work. There tend to be yearly reports, not always, it depends on what's written in the agreement, but always a final report will be required. And you usually want to plan for 6 months for that final report to be written, finalized, edited, all turned in and done. Once the agreement ends, that's it. You can no longer, it's done. So if your report is only a draft, that's how it's going to stay, which is not really something that you want to do. Agreements can be amended. There are things that happen in life and require an extension. And so if it looks like you're gonna need an extension on your agreement, you kind of start planning for that about a year before the end date of the agreement. And so with that, really quickly, that's how we are allowed to work and collaborate internationally. Yes?
The typical timelines for the cooperative research agreements, the grants, and the,
Sure.
yeah, those three.
Cooperative the CRADAs are similar to this. They're similar but different. We're very new at executing and creating the actual cooperative agreements. And so I don't have a hard number to give you, but you can count on like a year to get that CRADA in place. The cooperative agreement is a contracting avenue. That's gonna, there's different aspects to that too, but if there's already a cooperative agreement in place, in theory, it could just take a couple months. If you have to create a whole new cooperative agreement, it could take a year or more, okay? For a CRADA, you can think about probably a year or more. It depends on that front end work with the engineers, getting all that paperwork done and their brains to paper. And then for grants, the grant process is very simple. We work with AFOSR quickly, and if we contact the program manager and say, hey, we want to work with this professor, we can send money. If it's available, we can just send money right away. AFOSR gets it on contract, or they might already have a contract going, and we just do an ad funds, and it's immediate. Otherwise, it's a few months.
So this is maybe not a quick question, but can you comment about how the iCreative program or some of these other programs of non-government agencies intersect with ITAR compliance?
Oh yeah, ITAR. So ITAR, that don't know, is International Trade in Arms Agreements or restrictions. So that is all tied in with the paperwork and the licenses. It just depends on what the situation is. I think for companies need to, you know what, I'll talk to you offline about that because it's complicated and I don't want to misspeak and be taped. So,
time for one more question.
Thank you. I was just curious about what drives the need for the CRADA or the iCRADA to be equitable in benefit to both. I can understand it is nice to have, but if I'm willing to say, willing to give more than a return, why does AFRL insist that it has to be equitable?
it's more, so in general terms, the government cannot accept favors, right? And so for our defense purposes, it's got to be like, we're getting something and you're getting something of mutual benefit. And that's true for all the agreements. And I think we just can't, someone can't just say, hey, I'll give you 80% and I'll only need 20% from you. Well, that's great, but that would indicate we would owe you a favor later, and the government doesn't want to sign up for that. It's fair across all boards.
All right, with that, yeah, let's thank Becky again. Great talk, great discussion. All right, I know we're going to be swapping computers now, but as we begin that, we're going to highlight a couple of our researchers that are been funded by our partners at AFOSR. So first up is a true pioneer in the quantum networking area, Professor Saikat Guha, who's director of the Center for Quantum Networks, a 10-year center funded by the National Science Foundation Engineering Research Center. This is one of the centers funded under the National Quantum Initiative Act. Professor Guha is a professor with the College of Optical Sciences at the University of Arizona in Tucson. His background lies at the intersection of information theory and quantum optics, so certainly near and dear to the information directorate here. He received his PhD from MIT in 2008, and some of his early work included work at BBN Technologies in the Quantum Information Processing Group, which he started in 2009. I've certainly followed his career for many years, and it's a true honor to have him speak to us today. Thank you.
Thank you very much for that. Thank you for the invitation. It's great to be here. Wonderful to be in person and seeing so many colleagues after a couple of years of isolation. I will talk to you about some work we have been doing at the University of Arizona on photonic sensing and imaging technologies, work funded by mostly DoD-funded work, DARPA, AFOSR, and the Office of Naval Research. Time permitting, I will give you just a glimpse of what we just heard about the Center for Quantum Networks. This is a 10-year center funded by the National Science Foundation. It's a concerted effort to develop basically all technologies, the entire technology stack to upgrade the internet to be able to carry qubits. So I will start with passive imaging, where the light that you're collecting, say telescopy or biological imaging scenarios like in fluorescence spectroscopy, it's classical light. But any classical light has a quantum mechanical description. Turns out that the quantum mechanical description of the light in passive incoherent imaging is a multi-mode, phase insensitive, zero mean Gaussian state. It doesn't mean much to a classical optical theorist, but once you cast that light in its quantum mechanical language, you suddenly have access to a lot of very powerful tools from quantum estimation and detection theory that can tell you what is the best way to measure that light if you know something very specific about what you're trying to gather from that light. All right, so that will be my first topic. So this is just a cartoon showing that there's the information content in the scene that you're trying to discern. It drops through various stages of the imaging system. Okay, so once you collect the light from your aperture, let's say of a telescope or a microscope, there's a certain amount of information that that light contains. And the moment you detect that light is the point where you go from that information being in the optical domain to it being in the electrical domain. So from quantum to classical. And usually turns out that in the traditionally unresolvable regimes, that drop in information is a huge drop. And that's because the detection that we are doing is the wrong kind of measurement. It's not ideally suited to the thing that you're trying to discern from that information. So there's a lot of innovation that has happened in the field of optics, in computational imaging particularly. And of course, there's a little bit of drop of information that happens because you've chosen a particular kind of post-detection signal processing. So our focus in this work has been to think of what we can do to that light before you detect it to increase the information content that you can gather. Okay. So with that, let me go to a very, very simple example that we started out, this was 5 years ago on a DARPA seedling project with DSO. 2-point stars. So you're looking at a binary star far away, and you're trying to estimate the angular separation between them, theta. So when that angular separation, theta, becomes much smaller compared to the Rayleigh length, or lambda over d, lambda being the wavelength of the light and d being the diameter of the entrance pupil of your aperture, what happens is that the point spread function, the intensity signature that you get on your camera on the traditional image plane, they come so close together that you can't tell them apart. So now mathematically, if you write down the mean squared error of estimating that angular separation from even an ideal focal plane array, a Poisson short noise limited ideal detector, direct detection receiver, which is what we would use in a traditional camera or a telescope, If you can write that as something like basically you could write it as 1 over n times a quantity called the Fisher information, and this n is proportional to the integration time. So and j of theta is a quantity that determines how well can you estimate that parameter. So this j of theta, this Fisher information, drops very rapidly to 0 when your theta, which is plotted on the x-axis in the units of lambda over d, falls below 1 or falls around 1 or 2. So you can see when this j of theta is very small, this n is your integration time. So you can always still drive the mean squared error down to as small as you wish, but you'll have to integrate for a long, long time. There was an IRPA program called the AMON-HEN program, some of you may know about, that was about detecting dimly lit objects in geostationary orbit. And they would actually integrate for days at a time to try to image some objects. So you can image, if your CONOPS permits you to integrate for long, you could still get your mean squared error down to very small. Turns out that there's a very surprising result that came out from some work that Man-Kei Sung did and work we did concurrently, that if you ask the question that what is the best possible measurement permissible by the laws of physics if you were just trying to estimate the angular separation of those two stars, then it turns out that this Fisher information doesn't drop at all. It stays flat. It's a very surprising result, which meant that you could do something to that optical field before you detected it to get that information as precisely as you would if that angular separation was bigger. And the thing that you have to do before that detection is a mode transformation. You have to do a spatial mode rotation on that collected light. You have to detect photons, but not in a standard pixel basis, but in this case, in a Hermite-Gauss modal basis for a Gaussian aperture, or the Sync-Bessel modal basis if you had a hard aperture. And even if you had a mode sorter, a binary mode sorter that sorts the fundamental mode, the point spread function mode, from the rest of the light, even that has a performance in terms of Fisher information that gets very close to this quantum Fisher information limit in the very small separation regime, which basically tells us is that there is when the object becomes very small, traditionally unresolvable, there's a lot of light in that point spread function mode, no matter what object you're looking at. It looks like a big blur, a Gaussian blur. So if you can take that light out and look at the rest of the light, there's a lot of information about the thing that you're trying to see in the photon detection statistics of that other bin. That's just the intuition, and there's a lot of mathematical details behind this. Then what we did was we looked at what is the fundamental limit of the Fisher information for estimating not just the separation of two-point sources, but also the centroid of the two-point sources. Because one of the things that was assumed in Man-Kei Sung's original paper was that he knew the exact center of the two-point sources that you were looking at, which will never be the case, right? So it turns out that for estimating the centroid, just using direct detection is pretty good. It is not quantum optimal. In this paper, we showed that there's a two-stage spatial mode demultiplexer that is truly quantum optimal for centroid estimation. But we said that why don't we try something very commonsensical. What we did was that, let's say you're looking at a two-point source, you don't know where to look, you don't know the centroid, so you just turn on a camera, a traditional focal plane array, for some time, and try to gather where the centroid is, get a blurry image of the scene, and then during that integration time, you make a switch to a binary mode sorter, and then point that binary mode sorter towards the noisy estimate of the centroid you got from the previous stage. And you decide dynamically as to when to make that switch based on when you think that moving to that second stage is going to give you a better performance eventually, right? So, because if you spend the entire integration time doing direct detection, then of course you are doomed to the direct detection's performance. If you switch too soon, you will have a mode sorter that is pointed inaccurately. So there's an optimal point to switch. And it was a very classical calculation by my student Michael Grace. He did this work. And turns out that even without the prior estimate of the centroid, and this is true mean squared error normalized to the total photons integrated divided by the squared of the Rayleigh length lambda over d, over the entire sub-Rayleigh regime, there's a factor of 10 to 100x improvement in the mean squared error. So which means that it is that much smaller, that many fewer photons that you're going to need to integrate to get the same mean squared error performance compared to if the best possible focal plane array that laws of physics would allow. This was very promising, and this was it was a simple calculations, but this led us to so this was done on a seedling program that led to a DARPA DSO starting a whole program called Iambic. This was Joe Altipeter's program out of DSO. We were one of the performers in that team, my colleague Amit Ashok and his student Kwan Kit Lee, who did most of this work, along with my student Michael Grace. So DARPA gave us a challenge problem. They said, well, 2-point sources to toy a problem, let's make it a little bit more difficult. So they hired a T&E team, and their job was to generate randomly scattered point-like emitters in a tiny sub-Rayleigh field of view. So X and Y axis here are in units of lambda over D. And these black little dots that you're seeing are the point emitters that a T&E team would generate. And we would have to design a mode sorter, but this time, a mode sorter is an adaptable mode sorter. So you have a spatial mode sorter, you're detecting photons after the light goes through it, but based on the incremental click events, you get to change the modal basis in which you want to make the next measurement throughout the integration time. So we went back and used some very interesting theory on Bayesian quantum estimation that was developed by Stu Personic in 1973 on quantum limited minimum mean squared error estimation of a parameter with a known prior. I won't have time to go into the details of the mathematics. If you're interested, take a look at that paper. But if you look at this image here, the blue circles, so the only difference between the left and the right-hand side plot, the left-hand side plot, we are giving the prior information to the camera as to how many point emitters there are. So it will obviously always generate 3 estimates. The right-hand side, you're not telling the imager how many point sources there are. So black is ground truth. The blue circles is what is generated by a traditional camera. And the red squares are what are generated by our ideal mode sorter design. So it's obviously much, much better. I mean, we just patented this idea, and we just started building a mode sorter for a problem like this. So this is direct applications to storm microscopy. So if you know storm microscopy, you have this blinking fluorophores, and you turn down the duty cycles really low so that at any given point in time, you have only one blinking fluorophore that you image using a camera, and you integrate for a long time to image the biological tissue that you're trying to image. But now you get to turn up your duty cycle, so you can get at 4, 5, 6 emitters at the same time that you can localize very well. So you can maybe get into the domain where you can do live cell imaging, for example. Same sort of technique also applies in detection theory. So let's say you're trying to tell apart between a library of QR codes or barcodes, or irises, or license plates, or fingerprints. So we showed, and this will be appearing in physical review letter soon, that if you write down the probability of error of telling apart between a set of objects in passive imaging, and express that as e to the minus xi n, where xi is called the Chernoff exponent, and n is the total mean photon number you have integrated. So n is proportional to your integration time. Turns out that this xi for an ideal direct detection camera goes as gamma to the 4, where gamma is the angular extent or length of the object in units of lambda over d. Whereas with an ideal quantum limited receiver, which is in this case also happens to be a mode sorter, gives you a gamma to the squared scaling. So this can be a much more of a difference. So you can get a 2 orders of magnitude improvement in the integration time. We have built a mode sorter in the lab. This is not published. My student Itai Ozer, he did the experiment along with Michael and presented this at Clio. But this is in some unpublished data from just last week that we are just barely seeing about an order of magnitude improvement in mean squared error for that 2-point source problem with an unknown centroid. The way our mode sorter works is, this is not new. This has been done by people like Bob Boyd has done it, and many people in the community have done this. You can show that if you have enough stages of propagation of light through a phase spatial light modulator, interspersed with free space propagation through air, through Fresnel diffraction. Both of those two are non-commuting unitaries that you can stack together to get any unitary transformation on a set of co-propagating orthogonal modes. And we have developed an algorithm that can go backwards and tell you how to program those phases. And so here what I'm showing is that these are one of these 2 orthogonal modes. Yellow is 0 phase and purple is pi phase. And depending upon which one of these 2 mode patterns go through this SLM mode sorter, you get a tiny little light spot here or there. And this is the confusion matrix. So you can tell them apart. So switching gears, some work that we have been doing for Office of Naval Research on entanglement-assisted photonic sensor networks. there's a, so this original idea of using squeeze light for enhancing the estimation of a phase that goes back to work by Jeff Shapiro and Carl Caves and many pioneers in quantum optics. So they showed this, there are various versions of this result. And what I'm showing here is a phase conjugate interferometer. Phi and minus phi, phi is an unknown phase. And turns out that if you have a total mean photon number constraint of n, if you use a laser light probe and a homodyne detector, you get a scaling of the variance of the phase estimate to go as 1 over n. Whereas if I split that light, that energy into a squeezed light and a laser light probe, in an optimal fashion, your variance goes as 1 over n squared. So this is called a Heisenberg limited sensitivity. There is an extension of this result that came out from some work that we did in this paper, along with Chuntao Zhuang's work with Jeff Shapiro and some others, where we showed that if you had instead a collection of sensors, so think of an RF photonic sensor array, which is what I'm trying to show here. And each sensor is sensing a phase of an incoming field. In this case, it's a microwave field that is modulating an optical phase that you're reading out locally. If you're not interested in estimating each of those phases individually, but are only interested in a function of those phases. So in this case, let's say we are just interested in the angle of incidence of that microwave field or its center frequency. Then you can start with a single mode squeeze light and split it up into in an array of beam splitters to generate an entangled state of light, a continuous variable squeezed multimode entangled state, which then if you injected into each one of those sensors, instead of injecting individual squeezed light, you would get an additional improvement that comes from, that takes your variance from going from 1 over m, where m is a number of sensors, to 1 over m squared. So this improvement can actually be a lot more profound in situations like this. So Zheshen Zhang, my colleague at the University of Arizona, he led an experiment that showed this in proof of concept. And again, in an unpublished work, and we have extended this work to beam deflectometry. This was also done for an ONR project. It's a 6.2 project. We're working with Roberto Diener at ONR. The idea here is you have a multimode light on a diffraction-rated near-field propagation scenario. You're bouncing off light from over a nano cantilever, and you're trying to estimate the displacement, lateral displacement. So if you are just interested in estimating that lateral displacement of that beam, and if you write down the mathematics of how that affects your coefficients of the mode sorter at the output of the co-propagating spatial modes that light is carrying, it unfurls itself into a collection of Mach-Zehnder-like interferometers where there is a different phase modulation that happens on all of those modes, but it's a function of those phase modulations is that displacement that you're trying to sense. So all those co-propagating spatial modes become your sensor network. So they are the network of sensors that are trying to work together to estimate that small displacement. And again, here, if you used a single mode squeeze light source generated using a PPKTP crystal with a mode sorter that splits that light into and creates that multi-mode light in an optimal way, you can get within a factor of 10 to 50 enhancement in the sensitivity of sensing that tiny beam deflection. We have then gone, so this is now coming to the AFOSR portion of the work that we just started out recently with Dr. Michael Yakes. And this project is looking at, now what happens if I had a multi-aperture system? Okay, we could go back and use the theory we developed for DARPA to ask the same question. I had a few different mirrors, few segmented mirrors. Let's say you get to collect all that light in one volume of space. You could still think of those multiple apertures as a compound aperture and use the same theory to find what is the optimal mode sorting, what receiver to do to get to the best possible performance. So we developed that. And now the next question is, what if those multiple apertures are not at the same location, or it's not practical to bring the light to one location? For example, in long baseline astronomy systems or distributed aperture systems that are far away. Then turns out that you can get the same quantum limited performance instead by pre-distributing entanglement to those sensor locations and use mode sorters locally and just use classical post-processing. And this work is not published yet. So I will not go into too much more detail on that. Last topic I wanted to touch and spend a couple of minutes on, and this is a topic that all of you, I'm sure, have heard of a lot, quantum radars. And it's it's a topic that has a bit of a love and hate relationship in the community. And I can tell you a little bit of the story of where things stand with quantum radars, and then I'll stop for questions. So this is a paper that Seth Lloyd did back in 2000. Oh, this should have been 2007. And a big group of people, I was at MIT at the time, Jeff Shapiro, we did at 2008. The question we asked is, you are trying to detect the presence of a weakly reflecting target embedded in a lot of loss and a lot of noise. So you're doing a hypothesis test problem, and so you're trying to minimize the probability of error. And this M is your time bandwidth product. So W is the optical bandwidth around the center frequency of your probe, and T is your probe duration or integration time. So M is the number of orthogonal temporal modes you can pack into that time bandwidth product. So it turns out that if you are in this really bad regime, so a lot of loss, very low brightness probe signal, for some reason you're constrained to be transmitting very low brightness signal. Maybe you're trying to be quiet and just whispering to the noise, and you have a high noise, thermal noise, which would not be naturally true for optical domain, by the way, but in a microwave domain, this could be true. In this, if you are in this regime, then if you look at this probability of error and write it as, with again a quantum Chernoff-like exponent as e to the minus m xi, where m is the time bandwidth product, so proportional to your integration time, this xi, there's a factor of 4 or 6 dB improvement you can get by using a spontaneous parametric down conversion source as compared to a laser light source of the same transmit power and bandwidth. Now, this obviously was a very limited ConOps, right? Because you're looking for multiple things. High loss is fine because standoff sensing is high loss mostly. Low transmitter brightness, well, maybe you're trying to be covert, undetected, LPD, LPI. But high noise was very hard to justify for optical frequency. So we did a paper on looking at microwave frequency quantum radars with Shabir Barzanjeh. Then we've worked very hard on finding receiver designs. So I found a receiver design that later Chuntao Zhuang improved on, and Zheshen did an experiment on using an optical parametric amplifier. And the more advanced receiver that Chuntao came up with uses some frequency generation and photon detection, which can in principle attain this full factor of 4 improvement. But in more recent work, we have now extended this to look at multi-object discrimination scenarios. Chuntao and Jeff did a very nice paper, this PRL, on Bayesian analysis of range estimation radar. In all of this work, so there's scenarios where you can get this factor of improvement can be higher than the 6 dB. You can get to 10 to 15 or 20 dB of improvement in different scenarios, but you still have to be in this high noise regime and this low transmitter brightness regime. So that prompted us to look specifically at covert sensing being one application of a quantum radar. And there are a couple of theory papers there, and there's just this experimental paper that just came out a few months ago, or last month actually, where the crux of the matter, I will spare you all the mathematical details. If I use a constant power transmitter, a probe, the mean squared error of sensing a parameter that you're trying to sense goes as 1 over the integration time, basically. So little n is the time bandwidth product. But if you can program your probe power in a way such that you will be provably undetectable, meaning your probing attempt is undiscoverable by a quantum powerful adversary. But if you want to do so, then your mean squared error still goes down with your probe duration, but it goes down as 1 over square root of the integration time. So 1 over square root of n. And this work actually has some mathematical underpinnings that my colleague Bulat Bash developed for quantum secured covert communications, which I will not talk about. So I already touched through all the application domains that some of this work could impact, so I will not read through this list. But I will tell you a couple of words about the Center for Quantum Networks. If you're interested, feel free to Google this or take a look at our website. It's a 10-year-long center, $50 million that National Science Foundation funded 2 years ago. I'm the director of the center with my colleague Dirk Englund. He's the co-deputy director along with Jane Baumbauer. She's the co-deputy director for societal impact research, and Julie Ems is the administrative director. I see a few company members who are part of our team who are here, so thank you for your support. We have a few more company members that I see. I don't have their logos who have joined our center since the time I made that slide. It's a 10-university center. MIT, Harvard, and Yale University are our core partners. and University of Arizona as the lead. And this program spans basically every aspect of quantum networking. So we have people working on material science research, developing new color center memories that have better properties at higher temperatures and better coherence properties, to spin photon interfaces, to error correction codes for entanglement distillation, and then a layer up to network routing algorithms. We heard a very nice talk from NYSTEC yesterday, so we have some overlap. And in fact, Stephanie Wiener happens to be on our external advisory board, so we have a close collaboration with TU Delft and many other centers. And up a level to network application layer. So there's a lot of interesting research. And one of the things that we are doing, which is pretty unique, is we have a whole team of researchers with background in law, social behavioral sciences, and economics, who are doing a very deep dive research on societal impacts of technologies that may emerge from quantum internet. Brian yesterday mentioned the MURI program that we have with Dr. Durya Consever. If you are interested in this, let me know. It's a it's a theory-heavy program, but there's an experimental component that Dirk England is leading on understanding the mathematics of large-scale entanglement. It's a very, very interesting program looking at measures of entanglement, to axiomatic studies, to different types of manipulating entanglement of different kinds. University of Arizona, we are building a new building called the Grand Challenges Research Building, which will be available in 2024. And the Center for Quantum Networks will be on the 4th floor of the building, so you're all welcome to come visit us. Speaking of workforce, this topic came up in this workshop a few times. So this fall, we are very happy to announce that we are launching a master's program in quantum information science and engineering. And these are our faculty members who will be teaching different courses. If you're interested, let me know. And finally, one piece of quick advertisement. There's a workshop that happened 2 times before this. So this is the 3rd edition of this workshop. Some of you know about this already. Workshop for quantum repeaters and networks. If you're interested in attending, this is in Chicago. Please let me know, or please feel to go ahead and apply. There are still a few slots open. So with that, I'll thank my research team and my sponsors. And if there's still any time, I'm happy to take some questions. Thank you.
Thank you.
It's a very interesting talk. I'm curious, for the first topic on modal imaging, can you comment on the role of aberrations in the system? And also, can you compensate for it? For example, including it in your prior as you, say, lock on to these individual spots?
Very good question. The question is, how do you take into account aberrations? The one kind of aberration that we are looking at is aberration that comes from turbulence. Right? For astronomical imaging, that's a huge one. The other kind of aberration we are looking at is clutter. So in all the examples I showed, if you remember, one of the things I assumed is that those point sources that DARPA TNE team gave us were the only thing in my field of view. That's never going to be the case in any realistic scenario. For aberrations of the former kind, you can fold in, for example, adaptive optics into your mode sorter. Because adaptive optics is nothing but a mode transformation, except that it's an adaptive process. So we are looking into how much improvement you can still get if you have a certain, say, a given Strel ratio of your adaptive optics system. We are also looking at incorporating some of that prior knowledge you have about the scene into our design of the modal imaging receiver itself. And finally, we are looking at different designs where you have a multi-stage receivers, where you say, for example, spend a little bit of time just detecting some kind of an aberration. And then you switch to a modal imaging solution that uses that pre-estimate to design the mode sorter optimally. So in fact, those are exactly the questions we are considering right now in the phase 3 of that DARPA IMBIC program, including things like motion blur. What do you have if your objects have extended objects that are not point sources and so forth? Question? Great question. Relative motion, not just motion blur, but also there is Doppler, depending upon the scenario. So all of those things are being taken into account right now. So we don't have any results that I could show you. The results that I showed are these. So this DARPA IMBIC program, so it's a DSO program. So the results basically show that there is that say a 2 orders of magnitude possible improvement in an idealized scenario. The question is, now, remember that 2 orders of magnitude, we are calculating our baseline, we are being very hard on ourselves as well. So the baseline is an ideal direct detection receiver, an ideal focal plane array. So the question is, when you incorporate some of the real life effects, how much of that improvement still persists? So those are, we are looking at those questions quite carefully.
One more question?
Oh. It's the exact same idea. So think of it this way: say your mean squared error in a constant power sensing, it would typically go as 1 over the mean photon number that you integrated over the integration time. So if you try to stay covert, let's say using the relative entropy criterion that Matthew Block and Bulat have used in their papers, you have to use the square root law for the modulation. So the mean photon number per mode has to go as 1 over square root of the total number of modes you intend to transmit over the integration time. And the moment you make that modulation, it shows up in mean squared error. That shows up in we have a paper with Matthew Block on the error probability exponent for a quantum radar if you're doing a hypothesis test. So it's basically the same square root law that shows up in sensing as well. So this paper that Christos is the first author on that did the theory work. Happy to talk more details if you're interested. Well, communications, I would say what I'm personally most excited about, and I did not talk about it today, we have a few papers on this, is on entanglement-assisted communications. So the same reason why quantum radar works in this entanglement breaking scenario, where the entanglement dies in the process of helping you, but you could not have had that performance without the entanglement to start with. The exact same reason, if you had a pre-shared entanglement, the sender and the receiver, and the sender is constrained to be sending very low power signals because it's whispering into the noise, maybe it's because it's trying to stay covert. And if you have a high background noise because maybe they're transmitting at a microwave or a long wavelength transmitter, in that regime, you can get a huge improvement in the communications capacity. In fact, that improvement is even much more pronounced than this factor of 4. And so we are looking at transmitter-receiver designs for that on a different NSF specialized project on that topic. Other than communications and sensing, I can't think of anything right now, but there might be scenarios, but I'm happy to discuss more.
Great, let's thank
Thank you very much.
Okay, a few more talks to go. This next talk is another highlight where a researcher has been funded by AFOSR previously. So I'd like to welcome Dr. Johan Jestin, who's the CEO and co-founder of KI3 Photonics, a Canadian startup focusing on the development of quantum resource distribution with the vision to adapt quantum technologies to actual telecommunications infrastructure. Dr. Jestin received his PhD in materials science from the University of Maine in France and has been a researcher since 2002. He is an authority on the realization of systems and devices for telecommunication applications, including optical amplifiers, ultra-stable interferometers, sources of optical frequency combs, including specialized fibers and integrated optics. Welcome, Dr. Jestin.
Thank you for the introduction. Thank you very much. And hello, everyone. So I hope you're doing great today. First of all, I'd like to thank the organizer for giving me the opportunity to be here today and present what KI3 Photonics is doing. So my name is Johan Jestin. I'm the CEO and co-founder of KI3 Photonics, company that is building photonic hardware for quantum communication networks, and in particular for the distribution of quantum information. So first of all, I would like to start with the definition of what is a quantum network. So quantum networks are designed to transfer quantum signals between distant locations. So in this case, in this type of definition, we could easily replace the word quantum with classical, and make the comparison with the classical network that we are using today for communication. So there is a big similarity between those two, but the way we're going to have to operate it and look at it are completely different. So what quantum networks are basically aimed for? So this is basically going to be a little summary of what we already saw in the last days during this conference. So one of the most important or most recent application that we have for quantum networks relates to information theoretical security. So you can think here about one very famous application, which is called quantum key distribution, which is basically the transfer of secure information between two distant users. But you can also go beyond this quantum key distribution with applications like distributed quantum storage, for example, but also bid auction that are secure between different users, or more exotic things like, for example, quantum money. Another very important application also where quantum networks are going to play a very important role relates to enhanced quantum computing power. So you have different processors that are linked together into the network, and through parallel processing, so you can increase the processing capability, let's say, and solve more complex problems. And finally, there is can talk about sensing, where the network of different sensors can improve the sensing capabilities. And for all of this to happen, we need to have enabling technologies like, for example, quantum sources, but also signal processing units, quantum memories and repeaters, technologies like multiplexing, transduction, new quantum algorithm, graph state synchronization, and so on and so on. So, one essential requirement when we talk about quantum networks, I think it's important to think about these three different cases, which is a quantum network, in order to operate smoothly, let's say, has to be a requirement of universality, which means the compatibility with many protocols and application cases. It has to be scalable, which means you have a compatibility with the current infrastructure that we already are using today, and also the network architecture. And finally, a transparency, which means that ideally we're going to have the coexistence of classical and quantum channels into the same network. For all of this to happen, we basically have different building blocks that can be divided in three different sections. There is the hardware that a lot of people are working on it. So it relates to photon sources, generation of entanglement, for example, quantum memories, transducers, quantum random number generators, current signal processing units, and so on. And we also have important things to complete in the software section, where you have to think about new architecture, prediction tools, stabilization platforms, and design tools for the network. And finally, all of this also has to be complemented by more theory, let's say, in order to have optimized protocols and find also new use cases for quantum networking. And an important thing also to consider in this case for the hardware, the software, and the theory is this has to be linked to a strong quantum supply chain. So we realized that, for example, on a 5-year quantum project, there is 60% of the time that is actually used for equipment sourcing and customization. 20% of the time is used for shakedown, and only 20% of the time of this 5-year quantum project will be used on data collection. So it's really important to reduce this time in terms of equipment sourcing and customization, with mass producible, low footprint and inexpensive hardware, but also compatible infrastructure that, hardware that is compatible with mature infrastructures and with which we can leverage already established degrees of freedom. So with all this in mind, we had the vision to build K3 Photonics with my co-founder and trying to focus on different, let's say, different sectors in order to have distribution of entanglement for multiple access points. So we want to move out from this point-to-point communication that we have, for example, in the first demonstration of QKD. Of course, we want to have low-cost implementation. It's always better. More resistant quantum signals when they travel around the network. And all of the hardware that we are using and everything that we do has to be fiber compatible. So it has to be easy to integrate with the current infrastructure that we have. So I want to go a little bit more into details of how we can encode the information with photons. So you can go with position and path, polarization, that is pretty famous, where you go vertical, horizontal polarization. You can go with frequency also, and arrival time. So what we choose at K3 Photonics is using frequency and arrival time. So it's basically to have frequency bin entanglement and also time bin entanglement. So the advantages are many to use those degree of freedom. It's, of course, the robustness. It's easily accessible. It's compatible with standard telecom components. Single spatial mode. It's scalable to higher dimension, and you can create more complex states. So it's basically what we did in this paper that we cited here by basically having creating hyper-entanglement and cluster states with off-the-shelf telecommunication components and integrated optics. So in this case, I'm really happy to show you what K3 Photonics is actually building. So this is one of our first products that we are actually packaging. It's called QCOM, and it's a frequency multiplex signal generator. So basically combines integrated chips with fiber optics components, and it enables the multiplexing and generation of pairs of photons over 50 different ITU channels. And basically those photons are generated over an optical frequency cone. So it can be used for faster key exchange rate. It's of course compatible with the existing fiber infrastructure. It's also efficient information traffic management. And it's also a low-cost approach because, for example, we don't have a big external laser that is going to have to pump your integrated optic chip, for example. So QCOM increases the efficiency, lowers the cost of, for example, QKD systems towards quantum network. So as I said before, so we can have first demonstration with QKD. So that's basically what we are doing, still doing in the lab. But we can see also beyond QKD with other use cases application. So another product that we are building is called CAVE, which is a quantum signal stabilizer. So it basically stabilizes quantum signals against environmental perturbation. This is basically a fiber-based interferometer for which you have a stabilization system that fit in a 19-inch rack mount. And this is actually tested by some of our partners in Caltech and Fermilab for QKD application, but also entanglement swapping. So can be used for highly stable temporal encoding. Again, it's compatible with the existing optical fiber infrastructure. You have minimal hardware requirement, and it's also a low-cost approach. So this is all the hardware part that we are building. And we are also working a little bit now on actually, we're working a lot on that. We are working on the design tools for quantum circuits. So this is a project that is actually financed by the US AFOSR. And we are doing this project in close collaboration with a partner, which is Quantum Bridge Technology. Quantum Bridge Technology is just like A3 Photonics, based in Canada. I forgot to mention that, but the company is based in Montreal, Canada, while Quantum Bridge Technology is based in Toronto. So it's a really great opportunity that we had this grant with the US OSR. And basically what we are doing is that we are studying graph states that are highly sought after quantum resources, rich in entanglement and compatible with several tool sets. And we are basically developing a flexible computational and theoretical framework for the study of graph states. So you basically arrive with one graph states, and then you're just wondering what kind of quantum circuit I should build to obtain these graph states. So you're putting everything into our software, and your software is going to give you different options of which kind of circuit that you can use in this case. So graph states are really, really important. We saw many talks in the last 2 days talking about graph states, and they address actually important challenge in quantum networking, but also in quantum computing. So in this case, I would like also to mention the importance of the quantum ecosystem and the partnership that we need in order to build this quantum ecosystem. So as I just mentioned before, so the grant that we are using is sponsored by the US OSR. We are collaborating with Quantum Bridge Technology. Also for the interferometer that we have, we are testing it with the Fermilab and also the University of Caltech. So we believe it's really, really important to build strong partnership for the quantum ecosystem. And also the fact that big players like Amazon Web Services and also Cisco are now entering into the quantum networking sector. I think we can see that something like happened also in the quantum computing industry with, for example, Google and IBM that are pushing for innovation, and then more startups are coming, more collaboration are coming, and more innovations are coming out of this. So we think that we're going to have big innovations more coming in the field of quantum networking. And also academic partners are going to play a very important role in terms of workforce training and product co-development. So in this sense, what we are trying to do with Quantum Bridge Technology is to build a quantum networking consortium. So we want to build the foundation of the quantum internet. And of course, we are looking for some potential partners in industry and academia. Also early adopters and investors. So what basically differentiates us from, let's say, more older quantum networking consortium is that we are basically using our technology which distribute entanglement over frequency comp, for example, for networking application, and the use of graph states to see how those graph states can be used for quantum memories and quantum repeaters, for example. So to conclude, I just want to say that we are working hard on the development of quantum hardware and now also more software tools. In order for quantum networking to be stronger, we're going to still need to be supported by a very strong supply chain. And the QNC, so which is the Quantum Networking Consortium, is now looking for some partners. So that's it with my presentation. I will be happy to answer your questions.
Thank you very much.
Thank you very much.
Making the trip. So earlier we heard about one of the AFOSR programs being the Windows and Science program, which allows researchers to travel to the US and work with our researchers and give talks. One of those researchers that has worked with us is Dr. Paul Haljan. He's an associate professor in the Department of Physics at Simon Fraser University, where his group focuses on working with trapped ions for quantum simulations, quantum state manipulation, and technology development for quantum information science applications. He has his Bachelor's of Science degree in physics from the University of Alberta, as well as his PhD in physics from the University of Colorado, where he worked with the Griffiss Institute. Please join me in welcome Dr. Paul Haljan.
Great, thank you. Just before I start, I want to thank the organizers and Windows on Science for the opportunity to speak to you and for organizing this lovely event, including, I think I can speak for all of us, the amazing lunches in an operational air hangar. All right, so today I want to give you a little overview of some recent work that we've been doing, looking at a phase transition, probing a phase transition in a trapped ion system in the quantum regime. So you can think about this as a quantum simulation, but it's not in any way related to quantum simulations that you encounter in a typical trapped ion quantum computer, where you're engineering the interactions in some Hamiltonian for the spins. This is something that's really intrinsic to the Wigner ion crystal structures of ions in an ion trap and a phase transition. In that case, this way. So just to start with that, so if you trap a number of ions in an ion trap, laser cool them, you'll form crystals. And so typically you'll form linear ion strings. So 1D ion strings is a linear ion trap. But if you add more ions, so you increase the density, or if you relax the transverse confinement, as we do, you will form 2D zigzag structures, like you can see here in this slide. And the transition between these, there's a whole hierarchy of transitions between crystal structures. This one happens, in fact, in the appropriate limit to be a second order phase transition, so a structural phase transition from 1D to 2D crystal structure. And just to show you a little animation, I guess you could call it, of 40 or 50 ions in our ion trap. Just do it once or twice. So you go from a linear string to a 2D structure. The ion string is non-uniform in density, so the transition happens at the center first. Like for any phase transition, you have an order parameter. That's simply the size of the zigzag structure. And there's been a range of work to look at equilibrium properties of the order parameter, dynamics. We've been involved in some of that. So for example, looking at nucleation of topological kinks as you quench this transition. All of this is really in the classical regime. What that means is the temperatures of the vibrational modes are 10, 20, 30 phonons average. So warm, so to speak. So after some of our initial work in this area, we got interested, what happens when you look at this transition in the quantum regime? You cross the transition in the ground state of motion. So this actually goes back to an early proposal by Alex Retzker. And the essential point is a second order phase transition. So as you cross the transition, you will form superpositions, Schrodinger cat superpositions of the two symmetry broken structures, zig and zag, for example. So this is something given to you for free with the ions in the trap. It's an intrinsic source and principle of entanglement here. So in the initial proposal, there's some applications for trapped ion double well interferometry for looking at effects like electric gradients that will bias the potential. Our primary initial interest is fundamental. Can we see these superpositions? And can we understand their decoherence? So for example, scaling with the number of ions, how big can we make these superposition states? If you compare to other Schrodinger cat superpositions that have been created in an ion trap system, these are a little unusual in the sense that we're really pushing the limits of coherence in the ion trap down to low frequencies. So the typical tunneling rate is 3 kilohertz. It might be on the order of an entangling gate, for example, in a trapped ion system. But it's much smaller than mechanical vibration frequencies in the trap, and certainly much smaller than 10 gigahertz qubit frequencies. So we're interested in seeing if we could get sufficient control. We had to develop quite a bit of technology around the system in order to realize this. So, and it ranges from new cooling schemes, so brought 3D Sisyphus cooling to an ion trap system, really to simplify cooling of all 3 n degrees of motion of an ion crystal. So all vibrational modes down to a few phonons of excitation. And this has been adopted in a variety of groups around the world, particularly for quantum simulations of large ion strings. We have our own version of high stability ion trapping, passive active stabilization, giving us good short, long-term stability. Something that's a little bit unusual actually in an ion trap is we use optical tweezer forces to optically control the potential. So optical tweezers focus down to the single ion site. And probably the most important thing though is we use spectroscopy and get precision of assessing the system from spectroscopy of the system. So just a couple points on that. In particular, oops, let's go back here. If we look at the variety of modes that you can probe. So we look at the transverse zigzag vibrational mode that you can see over there on the left of the screen. So we're particularly interested in probing this mode because it gives you order parameter properties, including energy level structure, the signature of the transition. It's this mode that actually becomes unstable when you cross the transition. It basically freezes to give you these zigzag structures. Spectroscopy actually gives you everything. Not only can we measure order parameter properties and dynamics, but our control parameter is really changing the trap potential, and we can assess that in situ by measuring what's known as the center of mass mode of the ion crystal to measure what we're doing to the ion trap itself. So spectroscopy is key. And so I'll just give you some few slides on some of the results that we had. And the first one is to show you the energy level structure that we've measured with spectroscopy. So the plot you're seeing is the first and second sideband as a function of the change in the transverse trap frequency. So it's about a range of 1 kilohertz on a 1 megahertz trap frequency, so about 0.1%. And if you start in the ground state, the first sideband tells you the energy level splitting to the first energy level. The second sideband gives you the energy splitting to the next energy level. And you see this characteristic dependence, in particular for the first sideband. You see that the frequency drops to 0 as you cross the transition. And basically, as expected, you form this double well at the transition. The tunneling barrier comes up, and the energy level splitting drops to 0, you get a degeneracy. So that sideband frequency goes to 0. It's just like in a quantum annealing experiment. So a couple points to make. It's only within about 100 hertz of the transition that you actually see a significant deviation from classical small oscillation theory. Just to give you a feeling for some of the stability we have, this data is taken over about 15 hours. It's quite stable. We're actually tuning things in the trap on the order, the point space in there, 50 ppm. We're changing a few hundred microvolts of the ion trap DC voltages while we have 1 kilovolt of RF present in the trap. So good long-term stability is crucial for this experiment. So the data is relatively good. We can fit it. One of the key things that we're interested in actually in assessing some of this data was initially looking at bias terms in the potential. So from a condensed matter perspective, for example, a cubic bias term changes you from a second to a first order phase transition. But in the context of double well interferometry, we'd like a very symmetric double well such that we don't suppress tunneling. And so you can fit this data. And in fact, for this, which I forgot to mention, is for 5 ions, you have quite good symmetry. So this is, on the right, is actually a numerical inference of what the double well looks like and the wave functions for the first 2 levels. The bias is 3 parts in 10 to the minus 7. So you need quite small biases in order to guarantee that the wave functions are reasonably symmetric. So another interesting feature, I said spectroscopy gives you everything. It's true in some sense. We're able to do something that's completely different from typical ion trapping experiment because of this phase transition. So in a typical quantum computing experiment with trapped ions, you're really just dealing, as far as the gates are concerned, with a whole set of linearized harmonic oscillators with equispaced energy levels. At the transition, the system is totally nonlinear. And what that does for you actually is when you're close to the transition, you can resolve sidebands starting from the different energy levels. And so this gives us a new kind of thermometry, actually, where we can measure, so you see there in the middle, populations in the different quantum levels. And probably one of the critical results that we get from that is over here on the right. Just focus on the top red data here. That's the population in the ground state. So as we cross the transition, we remain majority populated in the ground state. We're doing this adiabatically, including the optimum tunneling point there, around about 100 hertz below the classical critical point. And then after that, ultimately, it will become non-adiabatic. So I won't spend too long on this. I just want to mention some other things that we can do. For example, we've looked at 3, 4, 5 ions. And without maybe going too much into the detail, you see quite a change in the asymmetry in the system, in the transition. We understand what it is. It's due to imperfections in the trap potential. What's quite interesting, though, is that you go from 3 to 5 ions and you get a 100-fold improvement in the symmetry of the system without us doing anything to tune the trap. It's really solely due to, as you go to larger numbers of ions, it becomes better symmetry protected against imperfections in the ion trap. That's very useful because if we want to go to larger numbers of ions, for example, up to 10, we expect that we'll have a very symmetric double well to probe coherence effects. Okay, so where are we going next? From the spectroscopy, the width of the lines gives us some estimate of coherence close to the transition. They're short, half a millisecond. Our next goal is to do full T1, T2 characterization close to this transition to understand decoherence phenomena. Looking a little further to the future, in doing this experiment, we've been interested in some of the fundamental aspects of entangled state creation, but we've realized that the system is particularly useful, and we've used it in tuning up the system, to assess electric field noise in an ion trap system. So electric field noise is particularly, or is of direct relevance to entangling gate performance in a trapped ion quantum computer. And this, using this transition actually has a number of advantages for assessing electric field noise. I'll just give you a couple of them. The phase transition, very sharp feature, in this case in spectroscopy, a sharp spectroscopic feature. And And one advantage is that you get more than an order of magnitude increase in single shot sensitivity to trap potential variations compared to the standard way of measuring these things. Another advantage is with just small changes in the voltage in the trap, we can essentially spectrally resolve noise from DC up to RF. So we can get a very easy characterization of noise sources within the ion trap. And so we see these as some advantages of this technique. We're implementing some of these at room temperature in our simple trap setup with SFU. One of the reasons or interests I have in coming here to Innovare is the potential to extend these measurements to advanced ion traps and potentially cryogenic systems. So here. So I'm not sure if I've run over time, but maybe I'll come back to the conclusions. I want to make sure I recognize members of my group. I've been involved in some of this research. So at Simon Fraser University in Vancouver. And I'll just pop back to the conclusions just to end. So we've studied this linear zigzag transition for the first time in the quantum regime, demonstrated some first steps towards double well interferometry, some trapped ions, and then I mentioned some of these ideas of extending this or taking advantage of this system for electric field noise. So thank you for your attention.
Nice talk. Thanks, Paul. You may have said this, and I'm sorry if I missed it, but what do you expect for the T1s and T2s for this? What do you expect them to be limited by, and ultimately, how good do you think it could be?
Interesting question. Quite a bit. So at the fundamental limit for an ion trap, you actually expect limitation really to be the image charges in the electron. We're too far away at the moment from this size of trap. These orders of magnitude longer time. So we think that these are technically limited. So there's a range. There's a range of solutions to it. One is this is from these improvements in essentially DC electronics, filtering, and also actually worry about off-amp noise sources. But then there's the RF side. And so there's some potential there for going to cryogenic temperatures. I'd like to be able to get, longer than a few tunneling oscillations.
Great, thank you so much. And, folks ever have a chance to, if folks ever have a chance to be in Vancouver and visit Simon Fraser and see Paul's lab, it's well worth the trip. We've been there. So next up, I'd like to introduce Professor Herbert Fatso, who's an assistant professor of physics at the University of Albany. This fall, he'll join the faculty, moving over to Buffalo, so at UB. He has PhD at LSU and did a postdoc fellowship at Georgetown University, followed by a second postdoc at Ames Laboratory, part of the Department of Energy. In his research, Dr. Fatso studies the non-equilibrium dynamics of many particle quantum systems. He's particularly interested in light-matter interactions that are pertinent for quantum information processing. He studies the dynamics of correlated quantum systems out of equilibrium due to applied electric fields or abrupt parameter changes. Dr. Fatso.
Thank you for the introduction, and it's a pleasure to be here. I was commenting earlier that I think I've been at all of the 4 conferences that we've had so far, and by my account, it's gotten better gradually. So I think I'm looking forward to the next one. And also, in fact, I think my collaboration with the AFRL started at the very first conference. That's where we exchanged information with the quantum folks, and so that was where we initiated our collaboration. And I'll talk a little bit more about that during the talk. And so in terms of the talk itself, I want to tell you about some of the work I've been doing on optimizing like-matter interfaces for quantum information processing. And throughout this conference, we've heard quite a bit about some of the topics that I'm going to touch on, but I'll briefly touch on the hybrid platforms that potentially are going to be the future of large-scale quantum systems, and discuss some of the challenges that we will face at the interface of quantum optics and quantum information processing. And in particular, I'll focus on spectral diffusion and talk about how, by using external field control protocols, we're able to optimize two-photon interference by overcoming spectral diffusion. And then, of course, I will talk a little bit about my collaboration with the quantum group here at AFRL and some of the experimental realization of the protocols that we're contemplating. And so, you know, the most fundamental building block, of course, of quantum information processing platform is going to be a quantum bit. And the requirements for these have to be these so-called Los DiVincenzo criteria. And you have to have some type of a two-level system for which you can easily perform a set of operations, including state initialization. You have to have non-leaf coherences. You have to be able to realize a set of universal quantum gates. You have to be able to measure the state of the system very efficiently. And of course, you have to be able to scale this to a large number of qubits. And we've now had multiple realizations of qubits. And these are just, this is just a small subset of what we see, including, say, the trapped ions, the superconducting qubits, the quantum dots, the NV centers, and other color centers, and of course, the photons. And so, you know, when we look at the future, what we potentially see is that we may have to use many different platforms in order to realize these hybrid systems. And in this way, we'll be able potentially to take advantage of each of these qubits' best qualities. And so you can, for instance, imagine that you can use, say, superconducting qubits for computation, for information processing, and then you can use trapped ions for communication, right? And then you can use atomic clouds for quantum memories. Now, obviously, if you have these different systems, it's going to be imperative that you're able to implement optimal interfaces between the different systems. And so, you know, I've just picked a few of these kind of light matter interaction operations that we have in quantum information processing. And one of the key ones that we've seen already multiple times throughout this conference is the two-photon interference that allows for us to generate entanglement between distant quantum nodes, right? Where you take a photon from emitter 1 and a photon from emitter 2, and then you interfere them through a beam splitter. Another instance is going to be, something happens on these pictures. They did not look this way when I produced them, but in any case. Another instance is going to be because, you know, quantum information has to be managed differently from classical information. That goes without saying. The way that we implement classical memories is by simply, you know, redundancy, by duplicating information. And because we have the no-clone theorem in quantum mechanics, we cannot, in general, just reproduce an arbitrary quantum state. So one of the possibilities is going to be to capture a quantum state in the form of a photon state, right? And take advantage of systems such as these three-level systems that I'm showing here that are able to slow down a photon and store it within these systems in a controlled way. So that's another one of the photon-mediated operations that are going to be essential. Yet another one is going to be transduction operation, where you're operating with two different qubits that have different energy scales. And then you want to be able to transfer your quantum state from one qubit onto another while they have these different energy scales. I'm going to be focusing particularly here on this two-photon interference operation. And when we try to implement these operations, what we want most of the time is we want to have optimal spectral overlap between the emission spectra of the two quantum emitters that we're working with. And very often what you will encounter, unfortunately, is the situation on the left where you have very minimal spectral overlap between the two emitters. And that's going to be, you know, very pronounced when you're dealing with solid state qubits, right? if you take a solid state qubit in general, between your ground state and your excited state, say you're interested in working at some target frequency omega 0, most of the time you'll have some detuning with respect to that target frequency that you're interested in working at. And when that two-level system relaxes from the excited state to the ground state, you have this Lorentzian line shape for your emission spectrum. The peak of that emission spectrum is what you're looking at. And in this picture, this is an actual experimental measurement of the emission spectrum of an NV center. And vertically, what you see is the number of scans. So essentially, you scan it once, you come back, you scan it again, and you come back, you scan it again, and so on. And the darker shade is the peak of this Lorentzian. And what you see is that indeed, that peak is essentially wandering in a random way. That's spectral diffusion in order pictorially. And so this is going to be a challenge if you go in to implement a two-photon interference operation. The question we want to ask is, how do we optimize this? How do we overcome spectral diffusion? And are we able to, by overcoming spectral diffusion, optimize the performance of such a system in a two-photon interference operation? Now, one approach is obviously going to be to make our systems increasingly clean, as pristine as possible. But we have to realize that even in the most ideal situation, we will still have some amount of noise in our systems. So potentially, the protocols that we're proposing, they're not just to overcome the worst case scenario, but even in the best case scenario, they may still be able to be that last mile current, if you wish, right? The thing that allows for us to complete the trip. And so what we're going to be proposing is that we use an external field protocol to supplement the material engineering or system designing. And so the Hamiltonian that we're going to be looking at, I apologize for the way these equations look. And as you can imagine, they did not look this way when I produced them. So, in any case, I'll walk you through each of the terms. And so the first term is your two-level system. The sigma z term is your two-level system, and delta is the detuning. The second term is your bath of photons, and that's the photon degrees of freedom that are then coupled to your two-level system in the third term here. And finally, you have the driving field at some Rabi frequency omega x. And how the profile of that driving field is how you design your control protocol. And in the case that we're suggesting is omega x is going to be such that we impart on the two-level system a sequence of pi pulses that is periodic in time. And the period of this is going to be tau. In other words, we're going to apply a pi pulse, we're going to wait some amount of time tau, and apply another pi pulse and so on, and do that periodically. And what we're going to be looking for is the emission spectrum. So if I take the system and I start off with the excited state of my two-level system that's occupied, the ground state is empty, and all the photonic bath levels are empty. So what I'm looking for is what are the photonic modes that are then occupied as a function of time? When the system relaxes, where does the photon go? And so that's what this term at the bottom of the slide is looking at. What's the occupation of each of the bosonic modes, right, as a function of time? And so we solved this problem using a set of complementary methods just to check that each of them was performing appropriately. And also because we had to make, again, a set of complementary approximations depending on the methods that we're using. And so we had to use different methods just to make sure that the approximations were not leading to spurious solutions. And the bottom line is here's the solution that we obtained. And this solution here, this graph is showing the emission spectrum for multiple values of the detuning. And what you will observe if you look at this graph is that essentially this picture does not depend much on the detuning, right? You have a central peak that's at omega equals 0, and omega equals 0 here is being measured with respect to the pulse carrier frequency. Your pulse carrier is at omega 0, and that's going to be a reference for measuring every other energy level. So essentially your central peak is at the pulse carrier frequency. The pulse carrier frequency decides which is the frequency at which your emission is being, the bulk of your emission in any case, the bulk of your emission is being produced. And then you have these satellite peaks, but even the satellite peaks are mostly determined by the interpulse delay because the peak on the right is at pi over tau, and the peak on the left is at minus pi over tau. again, measured with respect to the pulse carrier frequency. You get a slight variation in terms of the amplitudes of the peaks as a function of the detuning, but the positions of the peaks themselves don't change, right? And so essentially what we can say from this picture is that the emission spectrum now is not depending on what the detuning is. So this protocol is essentially producing an emission that does not depend much on the environment. And this protocol has been tested experimentally already, at least in this instance where these researchers use a set of NV centers to measure a magnetic field, very weak magnetic field, because in the NV centers, your qubit is actually a spin 1 system. And so if you look at the Zeeman splitting when you apply a magnetic field, that Zeeman splitting is going to depend on the strength of the magnetic field, right? And so by looking at the absorption spectrum of this system, you can measure what the strength of that magnetic field is. Now, if you use a single NV, the signal is very weak. If you use an ensemble of NVs, the detuning that each of the NVs is going to see is different. So your absorption spectrum is very broad and you can't really tell where the emission is occurring. And that resolution then is going to behave like 1/T2 star. Now, to optimize the sensitivity of this probe, if you drive it in the way that we've just prescribed, by applying this sequence of pi pulses, now you refocus the absorption spectrum of each of the NVs in the ensemble in such a way that your sensitivity is now going to be depending on proportional to 1/T2 instead of 1/T2 star. So you get a boost in the sensitivity on these magnetometers. So that's for the emission spectrum. Now, of course, we want to now go ahead and test with the two-photon interference itself. What happens if I take two quantum emitters that have different emission frequencies and I perform a two-photon interference with these two systems? In principle, if the emission spectra are different, what you expect is a poor performance. And that's exactly what you see on the picture, in the picture on the left with no control. And the insert of this picture is showing you that you have very little spectral overlap between your two emitters. I'm looking at two emitters here, one that has frequency detuning delta 1 equals 3.0, and the other one has detuning minus 4.0, right? And so you have very little overlap between the two, very little spectral overlap between the two emitters. And that's the reason why your G2, your cross-correlation at the detectors is behaving so poorly. The picture on the right is what happens when you now drive these two emitters with your sequence of pi pulses. And if you look at the insert, what you see is that you enhance spectral overlap between these two systems, right? You know, going from very minimal 2 or 3% spectral overlap, now we have well over 70% spectral overlap between the two systems. And the result of that is that your G2 is now behaving more like what you would want if you try to entangle these two quantum emitters. Now, in these calculations here, what we considered is that we have a static detuning between the two emitters. If we have an actual solid-state system, the detunings are going to be changing randomly in time. So it was actually important that we go ahead and look at the case where we have explicit noise in the system. So we take a quantum emitter that's actually fluctuating around omega-0 as a function of time. So as you look at the horizontal axis, you're looking at the same two-level system, different snapshots at different times, and you see that delta is essentially changing randomly. And so this Lorentzian that you have is going to be moving all over the place. And so your emission spectrum for the system is going to be the mess that you see at the bottom there. And so what happens when I drive the system, and again, on the left here is the sequence of detunings that I'm simulating here. So the detuning is really moving all over the place. And on the right is the emission spectrum of the system. The dashed line is showing you what the emission would be if you did not control it, right? You have this broad, ill-defined Gaussian spectrum. But with the pulse, sequence, what you see is the different shapes depending on the interpulse delay. Bottom line is, once again, you get the central peak at the pulse carrier frequency, and you get the satellite peaks. And again, the positions of the satellite peaks are not random. They're set by the interpulse delay of your pulse sequence. And so this is already kind of taking this idealized initial theory towards something that's more realistic, right? Because now I'm looking at explicit noise, and I'm also looking at finite width pulses as opposed to idealized instantaneous pulses. So, you know, the next step is to look at explicit noise and look at two-photon interference. And once again, you see that unlike the situation without any control, where you have two quantum emitters that are sitting in very noisy environment in this calculation, right? You have emitter number one that has delta 1 of t and emitter number 2 that has delta 2 of t, both of which are very broad Gaussian distributions, right? Which, if you look at the G2s on the left, they behave very poorly. Now, if you look at the G2s on the right, when I apply the sequence of finite width, in this case, finite width pulses, you get a significant enhancement of the two-photon interference. So, you know, this is work that I've been collaborating with the quantum group here at AFRL towards realizing this experimentally. And as I was mentioning at the beginning of my talk, the collaboration was initiated at the very first of these workshops. And we found the VFRP program to be the right channel for me. So for the past 3 years, I've been coming back to the lab in the summer. And Innovare has just been, you know, for me, just the perfect platform. The lab has, you know, for somebody interested in the types of systems that I'm looking at, the lab has, you know, superconducting, trapped ion and photons. They have all the systems that you want to be interested in, and they're open and they're very accessible. And also the people in the lab are equally accessible. So everything has been made extremely, how can I say, easy in terms of this collaboration. And so we've been working together towards actually realizing these protocols experimentally. We have right now some idea of what the schemes would look like. And we've tested, again, relaxing some of the idealized lines of thinking in the theory, kind of making the protocol more realistic. And we've done some calculations that confirm that, you know, potentially this should be very doable. We see, at least for now, we see no reason why this wouldn't work experimentally. So we've tested this versus, you know, what happens if the Rabi frequency is not very high. What happens if the rotation is not complete? You know, you're trying to apply a pi pulse. What happens if you don't quite apply a pi pulse? And that's the picture, in fact, that you're looking at here on the right. Yes, it's degraded when you don't apply a pi pulse, but you have to go very far away from a pi pulse in order to see degradation of the G2s. Right here, you know, the bottom picture is looking at 60% of a pi pulse. And, you know, that's how far off of a pi pulse you have to go in order to see degradation in the outcome of these protocols. So this is actually quite encouraging. So we're looking forward to seeing this happen experimentally. And we've also looked at what happens if you drive the system not with the pulse sequence, but with some other form of shape of your driving field. Now, the last thing I want to mention is that you know, I've looked at this problem from the point of view of, say, you know, spectral diffusion. I have one quantum emitter and the emission is drifting randomly in time, but it's very easy to have an interpretation of this in terms of an ensemble of quantum emitters once again. You know, all I have to do is, now if you look at this picture, it looks like the same, but I'm looking at different emitters at the same moment in time. They have different emission frequencies. So the emission of the ensemble is a broad mess, and of course I can refocus. So here in this picture I'm showing, here's the emission spectrum of an ensemble that's distributed in a Gaussian way when I don't do any control, and the blue line is showing the refocused emission spectrum of the same ensemble. Now you see that you have the central peak, and the central peak in fact has the line width of a single isolated emitter in the absence of any noise. And that also indicates some things that you can do with an ensemble for quantum information processing, but I don't think I have a whole lot of time to discuss that. I'm going to go ahead and flash my conclusions, thank my collaborators, David Ashalm and Slava Dobrovinsky, with whom I initiated this research at the DOE lab, and then of course Kathy Yan and David Hocko at the AFRL here, and you for your attention. Thank you. Thank you.
All right, so we've reached the end, believe it or not, after 2.5 days. So I'm going to have Dr. Don Teleska come up here to help close this out for us. There he is, but before he comes up here, so hold on. All right, hold on. All right, so I want to quick thank you to everyone here. So a reminder, we have the tours of the labs. If you've signed up for those, love to have you see our facilities here. The summer soiree, as Melissa talked about later on. Stay tuned. We'll be announcing the date for 2023 very soon. We just have to do some final coordination on that, but we hope to have everyone back. We're going to continue to grow it. Thank you to all of our presenters, many of you who traveled very far distances to get here, all of our attendees, same thing. Especially want to thank our AFRL quantum team who really, I get up here to talk, but they did all the hard work behind this, especially people like Don Teleska, Kathy Soderberg, Laura Wessing, John Maggiolino, all those put so many hours into this. Becky, of course, for her work here as well. And then our NYSTEC team with Phil, Shay, Lindsay, Shannon, and GI. We've heard from Melissa quite a bit this week, but there's also Kelly, Amy, and Darren, of course, who did an amazing job. So thank you all. Let me call Dr. Teleska up, who leads our supervisors, our quantum information science technology. Thanks, Mike.
Thank you, everybody. Distinguished guests, participants, I'd just like to thank you on behalf of AFRL and the GI for making this 4th annual Quantum for International Conference a great success. Quantum information science is going to be a revolutionary technology, right? I'm talking to the experts, you guys know that. When fully realized, it's going to allow us to do things in fundamentally different ways, ways that right now we can't even imagine. Achieving a quantum-powered future requires exquisite control of the quantum world in order to build the necessary foundational technologies that we need to change the future. See, the reality is that QIS innovations are likely going to be the foundation of many unforeseen technologies, and therefore they're extraordinarily important for our economic and national security. The work you and your colleagues are performing right now are the underpinning research efforts that this future will eventually be based off of. See, achieving such a profoundly advanced future can only occur through international partnering and collaboration. See, that's why the AFRL finds this conference so meaningful and necessary. We implore you to explore how you can partner with us through the Innovare Advancement Center. It's a truly novel arrangement for AFRL engagements, something that I don't think exists in many places. So during your time here, I hope that you had fruitful conversations and that those conversations are going to bear the fruit of long-term R&D collaborations. And if you haven't had a chance to speak with anybody on my team, feel free to come up, talk to me. I'll give you my card. I like to be a conduit for information. So with that, I'd like to tag on to some of the thank yous that Mike started, but I would like to thank Mike for being such a genial host and for all the work that he's put into this over the last number of months. I'd like to thank our RI Director, Colonel Fred Garcia, Oneida County Executive Anthony Picente, Mayor Jacqueline Izzo, State Senator Joe Griffo, State Assemblywoman Marianne Buttonshaw, and Congresswoman Claudia Tenney for their in-person support of this conference. I'd also like to thank all of our speakers. You did a wonderful job and you had many engaging presentations. Your passion and enthusiasm for this technology was apparent throughout the entire event. I'd like to thank my team at AFRL who spent many hours planning and organizing to execute this event. I'd like to thank NYSTEC for their AV support. And finally, I'd really like to thank Heather and the entire GI staff. They did the yeoman's work of putting this all together. The GI has been an outstanding partner and a gracious host throughout the planning and the execution of Q4i. So I'm not sure how many of you are familiar with what a black swan event is, but by definition, a black swan event is an unpredictable event that is beyond what is normally expected of a situation, and it has potentially severe consequences. Black swans events are characterized by their extreme rarity, severe impact, and the widespread insistence that they were obvious in hindsight. Despite the association these events have with significant negative impacts, black swan events are not all crises per se. So if you consider these examples of notable black swan events, the digital age or the .com era, so that was the rise of the internet, the adoption of personal computing, mobile phones. That was a black swan event. The terrorist attacks on September 11th, 2001. The 2008 global financial crisis, or the Great Recession. History is going to look back on your successes here, when the work of the people in this room produces seismic changes that are going to usher in the QIS era. And history is going to consider this new era a fundamental example of a black swan event. And with that, I'd like to thank everybody for coming. I hope you enjoyed your time here. And on behalf of AFRL, thank you for your time and your support. Have a great day.